The interview question that ends most DevOps careers. Picture this: you are in the final round for your dream DevOps job. The salary is life-changing. The interviewer leans in and says, "Describe, in detail, how you would debug a Canary deployment on ECS that's failing due to a misconfigured health check, and what CloudWatch metric you would use instead." Your mind goes blank. That's not in the textbook. That's not in the certification. The problem: why most engineers fail in 2025. In 2025, companies are done with theory experts. They want battle-tested problem solvers. They are asking tough, scenario-based questions that separate the engineers who can talk about DevOps from the ones who can actually do it. The difference between, "I have read about it" and "here's the exact code and the architectural pattern to fix it," is the difference between a job offer and, "we will keep your resume on file." The solution: your new interview playbook. What if you could walk into that interview with the confidence of a senior engineer who has seen it all and fixed it all? Welcome to the ultimate AWS DevOps Masterclass. Over the next 20 episodes, we are going to solve 20 real-world, high-value pipeline failures, the exact scenarios recruiters and hiring managers are using to find top-tier talent right now. What you are going to master. 1. We will start with the fundamentals every DevOps engineer must know: fixing IAM permissions, solving S3 artifact errors, and managing environment variables. 2. Then, we will accelerate into the intermediate challenges you will face every day: defeating ECR auth failures, unsticking blue or green deployments, and mastering TERRAORM state locking to prevent catastrophic race conditions. And 3. Finally, we will conquer the advanced, career-making scenarios that secure the senior-level offers: architecting secure cross-account pipelines, fixing EKS deployment failures with IRSA, and implementing data-driven Canary analysis. For every single challenge, you are getting the error, the root cause, the exact code to fix it, and the pro tips that will make you the smartest person in the room. Let's get you hired. This is not just another tutorial series, this is your playbook for getting hired in 2025. If you are ready to stop memorizing theory and start solving the problems that companies will pay you top dollar for, you are in the right place. Let's dive into our very first scenario, the classic IAM access denied.
Scenario 1, the classic IAM access denied.
You have perfectly configured your source and build stages in AWS code pipeline. You commit your code, the pipeline kicks off, and then, a red light. Access denied. In an interview, could you explain the exact IAM policy needed to fix this? This is one of the most common issues in AWS DevOps. It happens because of the principle of least privilege. Code pipeline is the orchestrator, but it does not have inherent permission to trigger other services. It needs to be explicitly granted the authority to start a code build job. Before, the insufficient IAM policy. Disclaimer: always test code in a non-production environment. The code pipeline service role might have permissions for other tasks, like accessing S3, but notice the complete absence of any code build actions. This is why the pipeline fails.
Here's the real error message you will see.
Access denied exception: user not authorized to perform code build : start build. Blocked pipeline state. As you can see in this diagram, the process starts on the left with AWS code pipeline. It attempts to send a start build request, represented by the dashed red arrow. However, this request is intercepted and blocked by the IAM service, shown as the red shield in the middle. Because the pipeline's role lacks the necessary permission, IAM denies the action, and the request never reaches AWS code build on the right. After, the correct IAM policy. Disclaimer: always test code in a non-production environment. The fix is to attach a policy that explicitly allows the code build : start build action. This statement grants the necessary permission. This policy works by adding a statement with effect, allow, for the specific action, code build : start build. By attaching this to the code pipeline service role, you are giving the pipeline itself permission to start the build process. Successful pipeline state. With the correct policy attached, the flow changes completely. Code pipeline on the left sends the same start build request, but this time, when it reaches the IAM service, now shown as a green shield, it is validated and approved. The solid green arrow passes straight through IAM and successfully triggers the AWS code build project on the right, allowing the pipeline to proceed.
Pro tip: specify the correct role.
In an interview, clarify that this policy must be attached to the code pipeline service role, not the code build role. This shows you understand which service is initiating the action versus which service is executing the build. It is a key distinction.
Follow-up question 1. What if you grant code build : start build but the build itself still fails with an IAM error?
Answer: this means the problem has shifted. The code build service role is now the one missing permissions. It might need access to S3 to download source code, or ECR to push a Docker image. The initial permission issue is fixed, but the build's own execution role is insufficient.
Follow-up question 2. How would you improve the provided policy fix to adhere to the principle of least privilege?
Answer: you would change the resource * to the specific Amazon resource name (ARN) of the code build project you want to run. This prevents the pipeline from being able to start any other build project, tightening security.
Follow-up: curveball: your security team has banned wildcards in the resource ARN. How can you allow a pipeline to only start builds for projects tagged with environment = production?
Answer: you would add a condition block to the IAM statement. Inside the condition, you would use a key like AWS resource tag or environment production. This is an advanced technique that enforces tag-based access control, a modern security best practice.
Extension challenge: cross-account pipelines.
Let's take this a step further. Your code pipeline is in AWS account A, but for security reasons, the code build project must run in account B. How do you grant the necessary permissions now? Cross-account IAM architecture. This diagram illustrates the cross-account solution. On the left, within account A, we have the pipeline role. To grant access, this role sends a request using the sts:\assume role action, shown by the green arrow crossing the account boundary. On the right, within account B, the build role is configured with a trust policy. This policy explicitly allows it to be assumed by the pipeline role from account A, securely connecting the two services across accounts. Quick quiz: to give a role the absolute minimum permissions to read artifacts from S3 and push an image to ECR, what 3 specific IAM actions would you need? Post your answer below.
The takeaway.
Remember, AWS services need explicit IAM permissions to interact. For code pipeline to start a build, its service role needs the code build : start build permission. Always check the right role for the right action. Next, we'll tackle a subtle but common problem. Your pipeline fails because it cannot find its S3 artifacts, even when the permissions seem correct. Stay tuned for that fix.
Scenario 2, the silent S3 failure.
Your pipeline build stage runs perfectly, everything is green. But when the deploy stage tries to pull the artifact. Failure. The artifact is missing. This silent killer often is not an issue with your code, but a misconfigured S3 bucket. Let's solve it. This happens because S3 buckets are private by default. For a service like code deploy or another code build stage to retrieve an artifact, the bucket must have a policy that explicitly grants read access to that service's IAM role. Additionally, if the artifact is encrypted, the role also needs permission to decrypt it. Artifact access blocked. Here's the visual breakdown of the failure. On the left, we have the deploy stage, which needs the artifact. On the right is the artifact bucket where it is stored. The deploy stage sends a request, shown by the dashed red arrow, but it hits a wall, the red, locked icon in the middle. This represents the S3 bucket's restrictive default state. As you can see by the labels, both the getObject and KMS::decrypt actions are explicitly denied, blocking the request completely.
A vague but common error message.
Code pipeline could not retrieve the S3 artifact. Check the permissions on the artifact bucket. Before, the missing bucket policy. Disclaimer, always test code in a non-production environment. Often, the problem is an empty or non-existent bucket policy. Without any statements, the default deny all rule applies, and no external service can read the artifacts stored inside. After, the correct bucket policy. Disclaimer, always test code in a non-production environment. This complete policy has two parts. The first statement allows the specified IAM role to get objects from the bucket. The second, equally important statement allows that same role to decrypt the objects using the specified KMS key. This policy explicitly grants the principal, which is the ARN of your deployment stage's IAM role, the required S3:getObject and KMS:decrypt permissions. This opens a secure, specific pathway for that role to read and decrypt the exact artifacts it needs. Artifact access granted. After applying our policy fix, the situation is resolved. The deploy stage on the left sends its request, and this time, it passes through the now green, unlocked icon. This represents the updated bucket policy and KMS permissions. The labels now show green checkmarks for both getObject and KMS:decrypt, indicating the actions are allowed. The solid green arrow shows the request successfully reaching the artifact bucket on the right.
Pro tip, check S3 object ownership.
A classic interview, gotcha. If your policy is correct and it still fails, check the S3 object ownership setting. If it is set to bucket owner preferred, objects uploaded by other services might not be readable. Set it to bucket owner enforced to solve this.
Follow-up question 1. What's the most likely cause if the policy is correct but you still get a not found error?
Answer. This usually points to a simple typo. Double-check the artifacts section of your buildspec.yml file. A misspelled path or file name is the most common reason the pipeline cannot find an artifact that was successfully built and uploaded.
Follow-up question 2. Your code build runs in a private VPC. How does this affect its ability to access S3 artifacts?
Answer. If the code build project is in a VPC with no internet access, it cannot reach the public S3 API endpoint by default. You must create a VPC gateway endpoint for S3 and attach it to the VPC's route table. This provides a private, secure network path from the VPC directly to the S3 service.
Follow-up, curveball. How can you ensure that artifacts can only be read by a specific run of a pipeline and not by any other process?
Answer. You would add a condition to the S3 bucket policy. The condition would check if AWS:/sourceARN in the request context matches the specific ARN of your code pipeline. This is a powerful technique that locks down the bucket to only serve requests originating from your pipeline.
Extension challenge, centralized artifact store.
In many organizations, all artifacts are stored in a central S3 bucket in a dedicated, shared services account. How would your code deploy role in account A to get access to an artifact in account B? Cross-account S3 access. This diagram shows the cross-account architecture. The large box on the left represents account A, containing our deploy role. The box on the right is account B, which holds the central artifact bucket. For this to work, we need a two-way permission handshake, as shown by the labels on the green arrow. First, the IAM policy on the deploy role in account A must explicitly allow it to get objects from bucket B. Second, the bucket policy on the central artifact bucket in account B must explicitly allow access from the deploy role in account A.
The takeaway.
Remember, S3 artifact failures are almost always due to one of three things: an incorrect bucket policy, missing KMS decrypt permissions, or a network path issue from a private VPC. Quick quiz: to simply list the contents of an S3 bucket, which single IAM action do you need? It is not S3:getObject. Post your answer below. Next up, we will solve one of the most frustrating build failures: when your code works locally but fails in the pipeline because an environment variable went missing. Do not miss it.
Scenario 3, the vanishing environment variable.
Everything works on your machine. You push your code, the pipeline starts, and the build fails with an undefined variable error. It is a classic DevOps puzzle that trips up countless developers. Do you know the simplest way to fix this inside code build? This issue occurs because AWS code build runs in a clean, isolated Docker container for every build. It does not inherit any environment variables from your local terminal or the pipeline's host machine. You must explicitly provide any variables your build script needs, such as a node_env or a database endpoint. Build container lacks context. This diagram shows what's happening inside the build environment. On the left is a generic box for environment variables. On the right is the AWS code build container, which is trying to run a script. Notice the red dashed line between them, blocked by a large red X. This visually represents the failure to pass information. Inside the container, the script expects an environment variable, indicated by the red question mark in run script env equals, which ultimately causes the build to fail.
The build log might show an error like this.
Error, node_env is not defined, cannot configure application. Before, the unaware build spec.yml. Disclaimer, always test code in a non-production environment. The build commands reference a variable, $node_env, but nowhere in this file is that variable defined. Code build has no idea what value to substitute, so the variable is treated as empty or undefined. After, the correct build spec.yml. Disclaimer, always test code in a non-production environment. The fix is to add the env.variables section. This tells code build to inject node_env with the value production into the build environment before any commands are executed. Now the script will have the context it needs. The env block in the build spec.yml is the standard way to define static, non-secret environment variables. Code build processes this section first, making the variables available to all commands in the install, pre-build, build, and post-build phases. Build container receives variables. With the fix in place, the diagram now shows a successful flow. On the left, we have a build spec.yml file. A solid green arrow, explicitly labeled env.variables, points from this file directly into the AWS code build container on the right. Inside the container, the script's question mark has been replaced with the value production, which is highlighted in green, indicating the variable was successfully injected and the build can now proceed.
Pro tip, understand variable precedence.
In an interview, mention that environment variables defined in the code build project configuration, via the AWS console or CloudFormation, will override variables with the same name in the build spec.yml. This shows you understand how to manage configurations for different environments without changing the source code.
Follow-up question 1. How should you pass sensitive values like an API key or database password?
Answer. You should never put secrets in the env.variables section. Instead, use the env.secretsManager or env.parameterStore blocks in the build spec.yml. This allows code build to securely fetch secrets from AWS Secrets Manager or Parameter Store at build time.
Follow-up question 2. What if a value, like a Docker image tag, is generated in one pipeline stage and needed by the next?
Answer. This is a job for code pipeline variables. You must configure the build stage to export a variable to a namespace, and then the next stage can reference it using the syntax hashtag namespace.variablename in its configuration. This is how you pass dynamic data between pipeline stages.
Follow-up, curveball: you want to use a different set of variables for main and develop branches, but you only want one code build project. How do you achieve this?
Answer. You can use shell logic within the build spec.yml. Code build provides a default variable, codebuild_webhook_head_ref, that contains the branch name. In the pre-build phase, you can use an if statement to check this variable and then export the correct environment variables for that specific branch.
Extension challenge, centralized configuration management.
Your application now has 30 environment variables for dev, staging, and production. Managing these in the buildspec.yml is becoming messy. How would you design a scalable and secure solution to manage these configurations? Centralized parameter store strategy. This diagram shows a best practice solution. At the top, we have a single, central config store, using the AWS Systems Manager icon. From this central hub, 3 green arrows branch out, pointing down to 3 separate build environments: dev build, staging build, and prod build. Each arrow is labeled with a specific path, like get/config or dev/ or get/config or prod/, illustrating how each build pulls only the configuration it needs from the central store, keeping the process clean, secure, and easy to manage.
The takeaway.
Code build runs in an isolated environment. You must explicitly provide all variables it needs. Use buildspec.yml for static variables and integrate with parameter store or secrets manager for secrets and scalable configurations. Quick quiz: what is the exact syntax in a buildspec.yml to pull a secret named API key from secrets manager? Let me know in the comments. In our next video, we will look at a simple but critical error, when your pipeline fails because code build is trying to use the wrong runtime, like an old version of Node.js. It is a quick fix that every DevOps engineer should know.
Scenario 4, the runtime mismatch mystery.
Your new feature uses the latest JavaScript syntax. It works perfectly on your machine. You push it, the pipeline kicks off, and code build immediately fails with a bizarre syntax error. This is not a code bug, it is an environment problem. Let's fix it. This happens when your application code is more modern than the environment it is running in. AWS code build uses managed Docker images with specific versions of runtimes like Node.js, Python, and Go. If your project requires Node.js 18 but the code build project is configured to use an older image that only has Node.js 14, the build will fail. The before error diagram. This diagram clearly illustrates the conflict. On the left, a file icon labeled app.js represents your modern code, which requires Node.js 18. The arrow shows this code being sent to the AWS code build container on the right. However, the container is labeled old environment and prominently displays a Node.js v14 icon. The result is a large red syntax error explosion inside the container, showing the incompatibility.
You will see a frustrating error like this.
Syntax error, unexpected token. This happens when using modern features like optional chaining on an old Node.js version. Before, the outdated project configuration. Disclaimer: always test code in a non-production environment. The key issue is this line in the project's configuration, shown here as CloudFormation. The standard 5.0 image is several years old and does not include the modern runtimes needed for today's applications. After, the correct project configuration. Disclaimer: always test code in a non-production environment. The fix is to simply update the image to a more recent version. Standard 7.0 is a modern image provided by AWS that includes Node.js 18, Python 3.11, and other up-to-date runtimes, resolving the incompatibility. By updating the image identifier in your code build project settings, whether in the AWS console, CLI, or an infrastructure as code template, you are telling code build to use a newer, more capable build environment that matches your code's requirements. The after success diagram. After the fix, the diagram shows harmony. Your app.js code requiring Node.js 18 is still on the left. But now, it is being sent to a code build container on the right that is labeled Modern Environment and contains the correct Node.js v18 icon. The red error is replaced with a large green checkmark, indicating a successful build.
Pro tip, use a version manager file.
In an interview, mention that you would add an .nvmrc, for Node, or Python version file to your repository. This file declares the intended runtime version. It not only helps other developers but can also be used in your buildspec.yml to fail fast if the environment does not match.
Follow-up question 1. How can you use multiple runtime versions in a single build, like Node.js 18 and Python 3.9?
Answer: the standard code build images come with multiple runtimes pre-installed. You can specify which ones to activate in the runtime versions section of your buildspec.yml. This allows you to run Node commands and Python scripts within the same build phase.
Follow-up question 2. What if you need a specific tool or library that is not included in any standard AWS image?
Answer: you have two options. For simple tools, you can install them during the install phase of your buildspec.yml. For complex dependencies or to optimize build times, the best practice is to create a custom Docker image, install all your tools, push it to ECR, and configure code build to use that image as its environment.
Follow-up, curveball: a new security vulnerability is found in the Node.js version included in Standard 7.0. What is the fastest way to patch all your company's code build projects?
Answer: the fastest and most scalable way is to leverage infrastructure as code. You would update the image version in your central cloud formation or TerraOrm module. If you are using a custom ECR image, you would update the base image, rebuild, and push it. For a really fast fix while waiting for AWS to update the standard image, you could add a command to the install phase of the build spec to manually download and install the patched Node.js version.
Extension challenge: enforcing runtime consistency.
Your organization wants to ensure all new Node.js projects use the company-approved LTS version, for example, Node.js 18, and fail the build if a developer tries to use anything else. How would you enforce this across dozens of pipelines? The extension challenge diagram. This diagram shows a robust enforcement strategy. On the left, a developer commits code containing a project-specific buildspec.yml. This triggers a central CI/CD template pipeline. The first stage, labeled lint and validate, uses a script to check the runtime versions section of the submitted build spec against a centrally defined, approved runtimes list. A green arrow shows that if it matches, the pipeline proceeds to the build stage. A red arrow shows that if it does not match, the pipeline is immediately failed.
The takeaway:
A works on my machine build failure is often a runtime mismatch. Your code build project's image setting defines its environment. Always align this image with your code's runtime requirements by checking the official AWS documentation. Quick quiz: in a standard code build image, which buildspec.yml command would you use to see all the available Python versions? Let me know below. Next up, we will fix a deployment error that happens after a successful build. Your deploy script fails with unknown options because of an outdated AWS CLI. Stay tuned.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem solving, generally most asked, and system design. Required for your AWS and DevOps jobs interviews like AWS Cloud Migration Specialist jobs, AWS Cloud Financial Analyst jobs, AWS Solution Architect jobs, Cloud Security Engineer jobs, Kubernetes Admin or Engineer or Architect or Developer jobs, DevOps ISE Engineer jobs, DevOps Metrics and Observability Engineer jobs, DevOps CI or CD Engineer jobs, AWS DevOps Engineer jobs, Cloud DevOps Engineer jobs, AWS Java or Python Developer jobs, DevOps Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Scenario 5, the unknown option, CLI error.
Your deployment script uses a cool new feature of the AWS CLI. It runs perfectly on your local machine, which has the latest tools. But when you run it in code build, error, unknown options. This is a classic sign that your pipeline is living in the past. This error happens because the managed code build images provided by AWS come with a specific version of the AWS CLI. As AWS releases new services and features, the CLI is updated to support them. If your deployment script uses a command or flag that was introduced after the code build image was created, the older, pre-installed CLI will not recognize it. The diagram with CLI fail. This diagram shows the core of the problem. On the left, our buildspec.yml file is trying to run a modern command, highlighted in the bubble as AWS deploy new flag. This command is passed to the code build environment on the right. However, notice the environment contains a faded, outdated CLI icon labeled v1. The direct result is the red error message at the bottom, which explicitly states error, unknown option, new flag, clearly identifying the outdated CLI as the source of the failure.
The exact error in your build logs will look like this.
Unknown options, cache control, public, max age equals 315360000. Before, the unprepared buildspec.yml. Disclaimer, always test code in a non-production environment. This deploy command uses the cache control flag, a feature that might not exist in the default, older version of the AWS CLI provided in the standard code build image. The build spec assumes the CLI is up to date, leading to the failure. After, the buildspec.yml with CLI update. Disclaimer, always test code in a non-production environment. By explicitly updating the AWS CLI during the install phase, you guarantee that your build environment has the latest features and bug fixes, making your deployment scripts reliable and future-proof. The after diagram representing success. After applying the fix, the diagram shows a successful execution. On the left, our buildspec.yml has been updated, as indicated by the new green plus install phase badge. This change directly impacts the code build environment on the right. The old v1 CLI is gone, replaced by a modern, bright white CLI icon clearly labeled v2. Because the tool is now up to date, the command runs without issue, which is confirmed by the large green checkmark in the corner.
Pro tip, cache the CLI installer.
Downloading the CLI on every run can slow down your builds. In your code build project settings, define a cache for S3. Then, in your build spec, check if the zip file exists in the cache before downloading it. This can save 30 to 60 seconds per build.
Follow-up question 1. What is a more efficient, long-term solution than updating the CLI in every build?
Answer: the best practice is to build a custom Docker image. You would use a base image, like Amazon Linux 2, install the specific AWS CLI version and any other tools you need, and push this image to Amazon ECR. Then, configure your code build project to use your custom image. This eliminates the installation step and makes your builds faster and more consistent.
Follow-up question 2. How can you ensure your build uses a specific version of the AWS CLI, for example, 2.9.0, and not just the latest?
Answer: instead of downloading the latest zip, you would need to find the URL for the specific version you want from the AWS CLI documentation. Then you can add a check in your build spec, like AWS version grep 2.9.0, and fail the build if the version is not correct. This is crucial for maintaining stable, predictable environments.
Follow-up: curveball your company's security policy blocks all outbound internet access from code build containers. How do you get the latest AWS CLI into your build?
Answer: this is a common enterprise scenario. The solution is to have a separate, approved process that downloads the official AWS CLI installer and places it in a secure, internal S3 bucket. The code build project's IAM role would then be given permission to access that S3 bucket. The build spec would use an AWS S3 CP command to download the installer from the internal bucket instead of curl ing from the public internet.
Extension challenge: centralized tool management.
Your organization now has hundreds of build projects, and you want to ensure they all use a standardized, security-approved version of the AWS CLI, kubectl, and TerraOrm. How do you manage and distribute these tools without each team writing custom install scripts? The extension challenge diagram. This diagram illustrates a powerful, build image factory, pipeline. The process starts on the far left with two key inputs, a base Docker image and a versions.json configuration file. These are fed into the central golden image pipeline, which installs the tools and pushes the final image to the central ECR repo. This repository now holds our standardized golden image. From there, as you can see on the right, all the individual app build projects pull this same image, ensuring that every team uses the exact same, security-approved build environment.
The takeaway:
an unknown options error almost always means the tool in your CI/CD environment is older than the one on your local machine. Fix this by explicitly installing the required version in your build spec or, for a more robust solution, by using a custom build image. Quick quiz: besides the AWS CLI, what's another common tool you might need to install in code build to work with Kubernetes? Let me know in the comments. Now we are moving up to the intermediate level. In the next video, we will solve one of the most common Docker pipeline failures, the dreaded ECR authentication error. Do not miss it.
Scenario 6, the ECR permission denied roadblock.
You have successfully built your Docker image in code build. The final step is to push it to ECR, and then, bam! Denied, user unauthorized. Your IAM role looks perfect, so what's wrong? This is the most common Docker in CI/CD problem, let's solve it. This error occurs because there are two layers of permissions. First, the code build IAM role needs permission to interact with ECR::put_image, etc. Second, the Docker client running inside the code build container needs to be separately authenticated to the ECR registry. Without this second step, ECR rejects the push, even if the IAM role is correct. Diagram 1: ECR push blocked by author. This diagram breaks down the failure. On the left, our code build container is attempting a Docker push, as shown by the dashed red arrow. The request heads towards the ECR registry on the right, but it is blocked by the red authentication circle in the middle. The label on this circle makes the problem explicit, auth token missing crossmark. This shows that the Docker client inside the container is not authenticated, causing the push to be denied.
The infamous error message you will see is:
denied, user is not authorized to perform ECR::put_image on resource. Before, the missing login command. Disclaimer: always test code in a non-production environment. The script jumps directly from building the image to pushing it. The Docker daemon has no active session or token for the ECR registry, so the push is immediately rejected as an anonymous, unauthorized request. After, the correct authentication flow. Disclaimer: Always test code in a non-production environment. This two-step process securely connects the IAM role's authority with the Docker client's execution context. The token is short-lived, 12 hours, ensuring the session is secure. Diagram 2, ECR push succeeded. With the fix in place, the flow is now successful. Notice the new label on the code build container, Docker login executed. This action has transformed the red blocker into a green authentication gate, now labeled auth token provided white heavy checkmark. As a result, the Docker push command, represented by the solid green arrow, flows straight through this gate and successfully reaches the ECR registry on the right.
Pro tip, mention the prerequisite permission.
In an interview, show you understand the whole process by mentioning that the AWS ECR get login password command itself requires the ECR get authorization token permission on the code build IAM role. Forgetting this permission is a common follow-up mistake.
Follow-up question 1. What if your login command succeeds, but the push still fails with the unauthorized error?
Answer. This points to a conflict between the IAM role policy and the ECR repository's own resource policy. Check the ECR repository's permissions tab in the AWS console. It might have a policy that explicitly denies pushes from your code build role, which would override the IAM permissions.
Follow-up question 2. Your security team has enabled immutable image tags in ECR. Your pipeline runs twice and fails on the second push. Why?
Answer. Immutable tags prevent you from overriding an existing image tag. The pipeline is likely trying to push the same tag, for example, latest, twice. The fix is to use a unique tag for every build, such as the git commit hash, which is available in the code build _resolved _source _version environment variable in code build.
Follow-up, curveball. The Docker login command is now deprecated in favor of the Amazon ECR credential helper. How would you refactor your build to use this modern, more secure method?
Answer. You would configure the Docker daemon to use the helper. In your build specs install phase, you would install the Amazon ECR credential helper package. Then, you would modify the docker config file, /docker/config.json, to use ECR login as the credential store for your AWS accounts registry. This eliminates the need to run the explicit Docker login command in every build.
Extension challenge, multi-region image distribution.
Your application needs to be deployed with low latency to both the US and Europe. How can you efficiently get your Docker image into ECR repositories in both US East 1 and EU West 1 from a single pipeline run? Diagram 3, Automated Multi-Region Replication. This diagram shows the most efficient solution, ECR's cross-region replication. On the far left, the code build container performs a single Docker push action, targeting the ECR repository in the primary region, US East 1. Once that push is complete, the green dashed arrow, labeled Automated Replication, shows the ECR service itself automatically copying the image to the ECR repository in the secondary region, EU West 1. This is a highly efficient push once, distribute many model.
The takeaway.
ECR unauthorized errors are almost always about authenticating the Docker client, not just the underlying IAM role. Always precede your Docker push with the AWS ECR get login password Docker login command. Quick quiz: if you are pushing an image to a different AWS account, where do you need to add permissions? The IAM role? The repo policy? Or both? Let me know. Next, we will diagnose a tricky deployment issue, a blue or green deployment that gets stuck in progress and never completes. This is a classic interview question about health checks, so do not miss it.
Scenario 7, the never-ending blue or green deployment.
Your pipeline is executing a flawless blue or green deployment. The new green tasks are running, but the traffic shift is stuck at 10% for an hour. It never completes, eventually timing out and failing. Why is it stuck? This is a top interview question. This happens when the application load balancer, ALB, cannot confirm that the new tasks in the green target group are healthy. During a blue or green deployment, AWS code deploy waits for the ALB health checks to pass. If the ALB continuously reports the new targets as unhealthy, code deploy will not shift the rest of the traffic and will eventually fail the deployment. Diagram 1, Health Check Mismatch. Here is the visual of the problem. On the left, the application load balancer is sending out a health check. As you can see from the red arrow and its label, it is making a GET request to the default path, /. The request hits the ECS task inside the green target group, but notice the info bubble at the bottom, the actual health endpoint is at /health. Because of this mismatch, the task is marked with a red X as unhealthy, which stalls the entire deployment.
The status you will see in the AWS console.
Deployment failed, the new target group did not stabilize. This is usually because the health checks failed. Before, the mismatched target group, cloud formation. Disclaimer, always test code in a non-production environment. The configuration explicitly tells the ALB to check the root path, /. If your application is a single-page app or an API that does not have a route at the root, the ALB will get a 404 error, and the health check will fail every time. After, the correct health check path. Disclaimer, always test code in a non-production environment. The fix is to change the health check path to the actual endpoint your application exposes for health checks, like /health or /API or status. This ensures the ALB is checking the right place to determine if the application is healthy. By aligning the ALB's health check configuration with the application's actual health endpoint, the ALB can get a successful HTTP 200 response. This marks the new targets as healthy, allowing code deploy to safely complete the traffic shift. Diagram 2, Health Check Corrected. With the correct path configured, the diagram now shows success. The application load balancer on the left sends its health check, but this time, as the green arrow's label clearly shows, it is correctly targeting the GET/health path. The ECS task receives the request at the right endpoint, and as a result, its status changes to a green checkmark, healthy. This is the signal code deploy needs to proceed with the traffic shift.
Pro tip, check security groups first.
In an interview, state that before even looking at the path, you would first check the security groups. The ALB security group must have an outbound rule allowing traffic to the container port, and the container security group must have an inbound rule allowing traffic from the ALB's security group. This is the #1 cause of health check failures.
Follow-up question 1. Your health checks are still failing, but you have confirmed the path and security groups are correct. What's next?
Answer. Check the health check settings themselves. The timeout seconds might be too short for a slow-starting application. The app might need 5 seconds to respond, but the timeout is set to 2. Increasing the timeout or the health check interval seconds can solve this.
Follow-up question 2. How can you get more detailed information about why the health checks are failing?
Answer. The best way is to check the ALB's access logs, which can be enabled to log to an S3 bucket. These logs will show the exact response code, for example, 404.503, that the target is returning for each health check ping, giving you a precise reason for the failure.
Follow-up, curveball: a successful /health check does not guarantee your app can connect to its database. How would you design a deployment that waits for the database connection to be ready before shifting traffic?
Answer. This requires using code deploys lifecycle event hooks. You would add an after-allow-test-traffic hook that invokes a Lambda function. This Lambda function would run integration tests against the green tasks, including a test to query the database. The Lambda would only return a succeeded signal to code deploy if the database connection is healthy, ensuring a truly safe deployment.
Extension challenge: zero downtime database migrations.
Your new green deployment requires a database schema change. If you deploy the new code before the migration, it will fail. If you run the migration before deploying the new code, the old blue code will fail. How do you execute this with zero downtime? Diagram 3, Expand Contract Pattern for Database Changes. This diagram shows the 4-step expand and contract pattern for safe database migrations. In step 1, expand, we apply a backward compatible change, like adding a new column. In step 2, deploy green, we deploy our new application version. Both the old blue and new green fleets can coexist with the expanded schema. In step 3, shift traffic, we redirect all live traffic to the now stable green fleet. Finally, in step 4, contract, with no traffic on the old code, we can safely remove the old column, completing the migration without any downtime.
The takeaway.
A stuck blue or green deployment is almost always a health check problem. The holy trinity to check is, 1. Security groups, 2. Health check path, and 3. Health check timeouts. Mastering this is key to reliable automated deployments. Quick quiz, by default, what range of HTTP status codes does an ALB health check consider healthy? Post your answer below. Next time, we will solve a frustrating source control issue. Your pipeline is not triggering automatically when you push to GitHub. We will dive into webhooks and connection settings to fix it.
Scenario 8, the silent GitHub push.
You have just pushed the most important commit of the day. You open AWS code pipeline, ready to watch it deploy, and nothing happens. You refresh. Still nothing. The pipeline is just sitting there, completely unaware of your push. What's the first place you should look? This classic problem occurs when the communication link between GitHub and AWS code pipeline is broken. This link is a webhook, a mechanism where GitHub sends a notification to a specific URL when an event, like a push, happens. If the webhook is misconfigured, its security token has expired, or a network rule is blocking it, the notification never arrives, and the pipeline never starts. Diagram 1, Webhook Authentication Failure. This diagram shows the broken communication path. On the left, GitHub correctly fires a webhook post request, represented by the dashed red arrow. However, this request is blocked by the red shield icon, which, as the label clearly states, is a 403 forbidden/auth error. This block prevents the signal from ever reaching AWS code pipeline on the right, so the pipeline has no idea that a push occurred.
The error is not in AWS, it is in GitHub.
In your GitHub repo settings under Webhooks, you will see a red X next to a recent delivery attempt with a 403 forbidden response. Before, the broken connection state. Disclaimer, always test code in a non-production environment. Conceptually, the problem is a connection in an error state. This is often because the underlying OAuth token used to create the connection has been revoked or has expired, breaking the trust relationship between AWS and GitHub. After, the re-established connection. Disclaimer, always test code in a non-production environment. This process uses the AWS CodeStar Connections feature to securely handle the OAuth handshake. When you re-authenticate, it creates a fresh, valid token and uses it to configure the webhook in GitHub on your behalf, ensuring the URL and secrets are correct. Diagram 2, Successful Webhook Delivery. After recreating the connection, the flow is restored. GitHub on the left fires its webhook post, and this time, the solid green arrow passes straight through the verification gate. The green label, 200 OK/delivered white heavy checkmark, confirms that the message was received and authenticated successfully, allowing it to trigger a new execution in AWS code pipeline on the right.
Pro tip, use GitHub apps.
In an interview, mention that for organizational use, you would recommend using a GitHub app for the connection instead of a personal user account. GitHub apps have more granular permissions and aren't tied to a specific user who might leave the company, which is a more robust and secure long-term solution.
Follow-up question 1. The webhook has a green checkmark in GitHub, but the pipeline still does not start. What's the most likely cause?
Answer: this almost always means the webhook was delivered successfully, but code pipeline chose to ignore it. The most common reason is a misconfigured branch filter in the pipeline source stage. For example, the pipeline might be configured to only trigger on pushes to the main branch, but you push to a develop branch.
Follow-up question 2. How would you create and manage the GitHub connection using infrastructure as code?
Answer. You would use the AWS ::CodeStar connections connection resource in CloudFormation or the AWS_CodeStar connections_connection resource in Terraform. You create the connection resource with a pending status, complete the authorization handshake manually once in the AWS console, and then you can reference that connection's ARN in all your pipeline definitions. This makes the connection reusable and manageable as code.
Follow-up, curveball: your company uses a self-hosted GitHub enterprise server inside a private VPC. How can it send webhooks to the public AWS code pipeline service?
Answer. Since the private server cannot reach the public internet, a standard webhook will not work. The best solution is to change the pipeline's detection method. Instead of webhook, push, you would configure the source provider in code pipeline for the GitHub enterprise server to pull_for_ changes. AWS will then periodically pull your server for new commits, removing the need for inbound connectivity.
Extension challenge: advanced trigger filtering.
You want to improve efficiency. How do you configure a single pipeline to trigger on pushes to the main branch, but ignore pushes to all other branches unless they are for files inside a specific services or API/directory? Diagram 3, Conditional Pipeline Triggers. This diagram shows how to implement advanced filtering logic. A GitHub push on the left enters the decision flow. It first hits the branch is equal to main check. If yes, the green arrow shows it immediately goes to run pipeline. If no, the red arrow directs it to a second check, file path is equal to services or API/*. If this condition is met, the yes path also leads to run pipeline. Only if both checks fail does the flow follow the final no path to ignore push, saving unnecessary builds.
The takeaway:
if a pipeline does not trigger, the problem is almost always the webhook. Your first stop should be the GitHub repository's webhook settings page to check for delivery errors. If that's green, check your pipeline's branch filters. Quick quiz: besides branch name, what other Git-related attribute can you use to filter pipeline triggers? Let me know in the comments. Next, we will dive into a common build time error. Your application cannot access database credentials because it is being denied access to AWS Secrets Manager. This is a crucial IAM-related fix.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your AWS and DevOps jobs interviews like AWS Cloud Migration Specialist jobs, AWS Cloud Financial Analyst jobs, AWS Solution Architect jobs, Cloud Security Engineer jobs, Kubernetes Admin or Engineer or Architect or Developer jobs, DevOps ISE Engineer jobs, DevOps Metrics and Observability Engineer jobs, DevOps CI or CD Engineer jobs, AWS DevOps Engineer jobs, Cloud DevOps Engineer jobs, AWS Java or Python Developer jobs, DevOps Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section. These questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Scenario 9, the empty secret.
Your build script needs to connect to a database, so you have stored the password securely in AWS Secrets Manager. You reference it in your build spec, but the build fails with authentication error. When you check the logs, the password variable is completely empty. What went wrong? This is a classic IAM permission issue. Code Build provides a secure mechanism to inject secrets directly into the build environment, but this action is not permitted by default. The Code Build project's IAM service role must be explicitly granted the Secrets Manager get secret value permission to read from Secrets Manager. Without it, the secret reference fails silently, and the environment variable is not set. Diagram 1, IAM permission denied. This diagram shows exactly why the secret is empty. The Code Build container on the left attempts to make a getSecretValue call to Secrets Manager on the right. However, the request, represented by the dashed red arrow, is intercepted and blocked by the red IAM shield. This signifies a permissions failure. As a result, no value is returned, which you can see in the box below the container where db_password is just a question mark.
The build error might be subtle, like
fatal, password authentication failed for user because the password variable was empty. Before, the insufficient code build role policy. Disclaimer, always test code in a non-production environment. Looking at the policies statement, you can see it only allows actions for ECR and S3. There are no permissions related to AWS Secrets Manager, which is why the request is denied. After, the correct IAM policy. Disclaimer, always test code in a non-production environment. First, we ensure the original, necessary permissions for ECR and S3 are kept in place. The build process likely still needs these. Next, and this is the critical fix, we add a second statement. This new block explicitly allows the Secrets Manager getSecretValue action on the specific ARN of the secret we need, adhering to the principle of least privilege. By attaching this policy to the Code Build service role, you are giving the build environment itself permission to make an API call to Secrets Manager, retrieve the value, and inject it into the environment variable specified in your build spec file. Diagram 2, IAM permission granted. After attaching the correct policy, the flow works perfectly. The Code Build container sends its getSecretValue request. This time, the solid green arrow passes straight through the now green IAM shield, which validates the permission. The request successfully reaches Secrets Manager, and as the dotted return arrow indicates, the secret value is retrieved. This is confirmed in the box below, where db_password is now populated with the actual secret value.
Pro tip, distinguish between the secret and its value.
In an interview, clarify that the build spec.yml references the name or ARN of the secret, not the secret value itself. The IAM role needs permission to the secret resource. This shows you understand the separation between configuration, the ARN in your code, and runtime data, the secret value fetched by the service.
Follow-up question 1. What if the permission is correct, but you get a resource not found exception in the build logs?
Answer: this means the IAM permission is working, but the secret itself cannot be found. It is almost always a typo. You need to check the secret identifier in your build spec.yml and make sure it exactly matches the name or ARN of the secret in Secrets Manager in the correct region.
Follow-up question 2. Your secret in Secrets Manager is a JSON object with multiple keys, for example, username, password, host. How do you inject just the password value into an environment variable?
Answer: you use a specific syntax in the build spec.yml. Instead of just the secret's name, you specify secret name:JSON key. For example, db_pass, mysecret:password. Code build will parse the JSON and extract only the value of the password key.
Follow-up, curveball: how can you ensure that this secret can only be accessed by code build and not by an EC2 instance that has assumed the same role for debugging?
Answer: you would add a condition block to the IAM policy statement. The condition would use a global condition key like AWS called via with the value code build.amazonaws.com. This ensures the getSecretValue API call is only allowed if it originates from the code build service, effectively locking down access even if the role is used elsewhere.
Extension challenge: cross-account secret access.
For maximum security, your company stores all database credentials in a central security account. How would you configure a code build project in a developer account to securely access a secret owned by the security account? Diagram 3. Secure cross-account secret access. This diagram shows the required two-way trust for cross-account access. The process starts in the developer account. Step 1. The code build role must have an IAM policy allowing it to perform STS::assume role. This role targets the secret accessor role in the security account. This accessor role must have a trust policy, indicated by the trusts dev role label, allowing it to be assumed. Step 2. This secret accessor role needs its own IAM policy to grant it getSecretValue permission. Finally, the secrets manager resource itself must also have a resource policy attached that grants access to the accessor role, completing the secure chain of trust.
The takeaway:
empty secrets are almost always an IAM problem. The code build service role needs the secrets manager getSecretValue permission. For best practice, always scope this permission down to the specific secret ARNs your build requires. Quick quiz: what is the equivalent IAM permission needed to fetch a secure string from AWS Systems Manager parameter store? Post your answer below. Next time, we will debug a common infrastructure as code failure, a CloudFormation deployment that fails and rolls back, leaving you to decipher the error logs. Do not miss it.
Scenario 10, the dreaded CloudFormation rollback.
Your pipeline build completes, the deployment stage kicks off, and you see create_in_progress. Success. But a minute later, it changes to rollback_in_progress. Your deployment has failed. This is a core infrastructure as code problem every DevOps engineer must master. This error occurs when the AWS CloudFormation deploy command is executed without providing values for all the required parameters defined in the CloudFormation template. The template is like a function signature, it declares the inputs it needs. If you call it without providing those inputs, CloudFormation cannot proceed and safely rolls back to the last known good state. Diagram 1, CloudFormation parameter failure. This diagram shows the failed deployment flow. On the left, our CI/CD pipeline sends a deploy command to AWS CloudFormation, but as the label shows, it is only providing the template.yaml. Inside CloudFormation, the template expects a value for the env parameter, indicated by the red question mark. Because this value is missing, the deployment fails, resulting in the red rollback crossmark status being sent back to the pipeline.
You will see this in the CloudFormation Events tab.
Template format error, unresolved resource dependencies, ENV. Parameters must be specified for the template. Before, the unfulfilled template and command. Disclaimer: always test code in a non-production environment. First, we see the template itself. It clearly defines a required parameter named env. It does not have a default value, so one must be provided at runtime. Next, we look at the deploy command in the build spec. It correctly provides the template and stack name, but it is completely missing any mechanism to pass in a value for the env parameter. After, the corrected deploy command. Disclaimer: always test code in a non-production environment. The fix is to add the parameter overrides flag to the deploy command. This flag allows you to provide key-value pairs directly on the command line. Here, we are satisfying the template's requirement by setting env to prod. The parameter overrides flag is the bridge between your CI/CD environment and the CloudFormation template. It dynamically injects the required configuration at deploy time, allowing a single template to be used for multiple environments. Diagram 2, CloudFormation Parameter Success. With the fix, this diagram shows a successful deployment. The CI/CD pipeline on the left now sends both the template.yaml and a params.json file to AWS CloudFormation. The template's requirement is now satisfied, as you can see inside the box where parameter env is correctly set to prod. Because CloudFormation has all the information it needs, the deployment succeeds, indicated by the green, create_complete white heavy checkmark status.
Pro tip, use parameter files.
For interviews, say that for anything more than 1 or 2 parameters, you would use a separate JSON parameter file, for example, paramsprod.json, and pass it using parameter file //paramsprod.json. This separates configuration from the pipeline script, which is a key DevOps principle.
Follow-up question 1. How can you provide a default value for a parameter so you do not always have to specify it?
Answer. In the parameters section of your CloudFormation template, you can add a default property to a parameter definition, for example, default, t3.micro. If a value for this parameter is not provided during deployment, CloudFormation will automatically use the default value.
Follow-up question 2. How would you pass a sensitive value, like a password, to a CloudFormation stack without exposing it in logs?
Answer. You would set the noEcho property to true on the parameter in the CloudFormation template. Then, you would store the actual password in AWS Secrets Manager or SSM parameter store, as a secure string. In the template, you would use a parameter of type AWS:/SSM::parameter::value string to have CloudFormation securely fetch the value at deployment time.
Follow-up, curveball. How can you ensure a parameter value is valid, for example, that an env parameter is only ever dev, staging, or prod?
Answer. You would add an allowed values property to the parameter definition in the template. This is a list of all valid string values. If a user tries to deploy the stack with a value that is not in this list, CloudFormation will fail the deployment before it even starts creating resources, which is a powerful validation technique.
Extension challenge, managing stack dependencies.
You have a foundational network stack that creates a VPC and subnets. You have a separate application stack that needs to deploy into that VPC. How do you pass the VPC ID from the network stack to the application stack automatically? Diagram 3, CloudFormation Cross-Stack References. This diagram shows the powerful cross-stack reference pattern. The network stack on the left defines resources like a VPC and subnets. Crucially, it has an outputs section. The green arrow shows a value being exported from this section. The application stack on the right then uses the fn::import value function, as labeled on the arrow, to dynamically consume this output as an input for its own resources, like the ECS task. This creates an implicit, managed dependency between the stacks.
The takeaway.
A CloudFormation parameter error means you broke the contract of the template. Always ensure your deployment command provides all required parameters, preferably using parameter overrides for dynamic values or a dedicated parameter file for static environments. Quick quiz: what command do you run to see a preview of the changes a CloudFormation deployment will make before you execute it? Let me know below. That wraps up our intermediate scenarios. Now we are moving into the advanced section, starting with a complex but critical challenge for senior roles, making a code pipeline in one AWS account execute a build in another. You will not want to miss it.
Scenario 11, the cross-account chasm.
You are a senior engineer designing a secure CI/CD platform. For security and blast radius containment, your pipelines run in a central DevOps account, but the build and deploy actions must happen in separate production accounts. You set it all up, and the pipeline fails instantly at the first cross-account step. The error is stark: access denied. This is not a simple policy fix, this is about mastering the fundamental architecture of AWS security. This failure is by design. AWS accounts are hard security boundaries. By default, no principal in one account can affect a resource in another. To make this work, you must establish an explicit, two-sided trust relationship. First, the pipeline's role in the DevOps account needs permission to request access. Second, the target role in the production account must have a trust policy that says, "I am willing to grant access specifically to that pipeline role." Without both sides of this handshake, the connection fails. Diagram 1, Role Assumption Blocked at Account Boundary. This diagram clearly shows the failed handshake. On the left, inside the blue DevOps account, A, the pipeline role attempts to make an sts::assume role call. The request targets the build role in the orange production account, B. However, the request is blocked right at the account boundary by the red access denied shield. This visually represents that account B has not established trust, and is actively rejecting the connection attempt from the external principal.
The critical error you will see is
access denied, user, pipeline_role_ARN, is not authorized to perform sts::assume role on resource, build_role_ARN. Before, the missing trust relationship. Disclaimer: always test code in a non-production environment. This is the core problem. The trust policy on the build role only trusts the code build service within its own account. It has no idea that the code pipeline role from another account should be allowed to assume it. The door is locked to outsiders. After, the complete two-sided handshake. Disclaimer: always test code in a non-production environment. Part 1 of the fix is in the target account. We changed the principal to the full ARN of the code pipeline role from account A. This tells the build role, you are now authorized to be assumed by this specific external identity. Part 2 is in the source account. We must also give the code pipeline role an IAM policy that allows it to perform the sts::assume role action on the build role in account B. Without this, it would not even be allowed to make the request. This two-policy solution is the cornerstone of secure cross-account access. The identity policy in account A says, "I am allowed to knock on the door." The trust policy in account B says, "I will only open the door for you." Both are required for the connection to be established. Diagram 2, Successful Cross-Account Role Assumption. With the correct policies in place, the handshake now succeeds. The pipeline role in account A makes the sts::assume role call, and the solid green arrow shows it successfully connecting to the build role in account B. This is possible because the build role now has a valid trust policy white heavy checkmark. Crucially, the diagram shows the next step. The now assumed build role uses its own permissions to execute the code build::start build action on the code build service within its local account, completing the secure, cross-account workflow.
Pro tip: defeat the confused deputy problem with external ID.
In a senior interview, do not just stop at the trust policy. Mention the confused deputy problem, where a principal with permission to assume a role could be tricked by a third party into acting on the wrong resources. The fix is to add a condition to the trust policy that checks for an sts::external ID. Your pipeline would generate a unique ID for each run and pass it during the assume role call. This acts like a secret handshake, ensuring the role is only assumed in the context you intended.
Follow-up question 1. The role assumption works, but the code build job still fails with access denied when trying to download source from S3. Why?
Answer: this means you have successfully passed the first hurdle, authentication, but failed the second, authorization. The assumed role in the production account now needs its own IAM identity policy that grants it permission to perform actions like S3:getObject or ECR::putImage on resources within the production account.
Follow-up question 2. How do you pass a secret from the DevOps account secrets manager to the build job running in the production account?
Answer: you cannot pass the value directly. The secure pattern is twofold. First, the assumed build role in the production account needs an IAM policy allowing secrets manager get secret value. Second, the secret itself in the DevOps account needs a resource-based policy that allows the build role ARN from the production account to access it. This is a crucial use of resource policies for cross-account sharing.
Follow-up, curveball: how would you allow the pipeline to assume the role, but for one specific deployment, you only want to grant it S3 read-only permissions, even though the role normally has much broader permissions?
Answer: this is an advanced use case for session policies. When the pipeline makes the sts:"assume role API call, you would pass along a JSON policy document in the policy parameter. This inline policy can only further restrict the permissions of the assumed role for that specific session. You would provide a policy that only allows S3:getObject, effectively creating temporary, least privilege credentials for that single deployment run.
Extension challenge: the hub-and-spoke CI/CD model.
Your company has a central DevOps hub account and 20 spoke application accounts. How do you design a single, generic pipeline in the hub that can assume a standardized role, for example, CI/CD deployer role, in any of the 20 spoke accounts to deploy an application? Diagram 3, Hub-and-Spoke CI/CD Architecture. This diagram illustrates the enterprise-grade hub-and-spoke model. At the center is the DevOps hub account, containing a single, master code pipeline. From this hub, green arrows representing sts:"assume role calls radiate outwards to multiple spoke app team accounts. Each spoke account contains a standardized CI/CD deployer role that trusts the central hub. This architecture enables centralized management and governance of pipelines while delegating execution permissions to the individual application accounts, achieving both consistency and secure isolation.
The takeaway:
cross-account access is a foundational AWS security pattern, not a bug. It requires a deliberate, two-sided handshake, an IAM policy on the calling principle allowing sts:"assume role, and a trust policy on the target role specifying which principle is allowed to assume it. Mastering this is non-negotiable for senior roles. Quick quiz: what is the key difference between a roles trust policy and a resource-based policy, like on an S3 bucket or a secret? Let me know in the comments. Next, we will tackle a notoriously difficult problem that plagues infrastructure as code: intermittent pipeline failures due to race conditions when multiple people run Terraform apply. We will solve it with state locking.
Scenario 12, the Terraform race condition nightmare.
Monday morning. 2 developers merged their approved pull requests. Both pipelines kick off to run Terraform apply. One pipeline succeeds. The other fails spectacularly. Worse, a check of the AWS console reveals that the successful deployment is now missing resources, and your infrastructure is in a broken, unknown state. This is not a code bug, it is a critical failure in your IAC workflow, and in a senior interview, you must be able to solve it architecturally. This catastrophic failure is a classic race condition. Terraform relies on a state file, .state, as its single source of truth about your infrastructure. When 2 apply operations run concurrently without a locking mechanism, they both read the same initial state file. Both calculate changes, and then both try to write an updated state file. The last one to write wins, completely overwriting the changes made by the first, leading to a state file that no longer matches reality, a phenomenon known as state drift. Diagram 1, State File Race Condition, No Lock. This diagram perfectly visualizes the race condition. At the top and bottom, CI/CD pipeline A and CI/CD pipeline B start their runs. Both begin by reading the same initial state, labeled read v1, from the central Terraform.state file. The problem occurs when they try to write their changes back. The orange arrows, labeled write v2 and write v3, converge on the state file simultaneously, resulting in the red conflict explosion. This collision means one pipeline's changes will be lost, corrupting the state.
The error is often indirect and confusing.
Error: provider produced inconsistent final plan. When expanding the plan for each resource to include new values learned so far, provider to provider changed the planned action from create to update. Before, the unsafe S3 backend. Disclaimer: always test code in a non-production environment. This configuration correctly sets up a remote backend in S3, which is the first step for team collaboration. However, it is dangerously incomplete. S3 provides a shared location for the state file but has no native, built-in mechanism to prevent two processes from writing to it at the same time. After, the production-grade locking backend. Disclaimer: always test code in a non-production environment. This single line is the architectural fix. By adding dynamod_table, we are telling Terraform to use a DynamoDB table as a distributed mutex, a locking mechanism. Before any read or write operation, Terraform will attempt to acquire a lock by writing an item to this table. If another process already holds the lock, it will wait, thus serializing the operations and preventing the race condition. This S3 plus DynamoDB combination is the industry standard for building a robust, team-safe Terraform backend on AWS. S3 provides durable, version storage for the state file itself, while DynamoDB provides the atomic, conditional writes needed for a reliable, high-performance locking system. Diagram 2, State locking with DynamoDB. With the locking mechanism, the process is now orderly and safe. The flow begins with pipeline A. Step 1, it sends an acquire lock request to the lock table, DynamoDB, which succeeds. Step 2, now holding the lock, it safely reads and writes to the state file, S3. Meanwhile, pipeline B attempts to start. Step 3, its request lock is denied, and it enters a waiting state. Only after pipeline A completes step 4, release lock, can pipeline B acquire the lock and proceed, ensuring all operations are serialized.
Pro tip: know how to break the lock.
In a senior interview, they will ask about failure modes. What if a pipeline crashes and the lock is never released? The answer demonstrates true operational experience. You use the CLI command Terraform force unlock lock_ID. You would first find the lock ID from the error message or by inspecting the DynamoDB table, and then manually release it. Knowing this command proves you can recover from a failed run without destroying the state.
Follow-up question 1. Why is S3 object versioning not enough to solve this problem on its own?
Answer: S3 versioning is a reactive, not a proactive, solution. It can help you recover a previous version of the state file after it has been corrupted, but it does absolutely nothing to prevent the race condition that causes the corruption in the first place. State locking is the essential proactive mechanism.
Follow-up question 2. Your team uses TerraGrunt apply all. How can race conditions still occur even with DynamoDB locking?
Answer: this is an advanced problem. TerraGrunt apply all runs multiple modules in parallel. If two different modules, for example, Service A and Service B, both have a dependency block that references the same output from a foundational module, for example, VPC, they will both try to read the VPC state file concurrently. TerraGrunt is smart enough to handle this for reads, but if they tried to modify the same dependent resource, you could still have issues. The solution is careful dependency structuring and potentially using TerraGrunt's dependencies block to create an explicit execution order.
Follow-up, curveball: how would you implement a break glass procedure to allow an authorized engineer to bypass a stuck state lock in a fully automated, auditable way?
Answer: you would create a break glass IAM role with a strict permissions policy that only allows dynamod:delete item on the lock table and S3:put object on the state file. Access to assume this role would be controlled by a system like AWS IAM Identity Center with a time-bound, approval-based workflow. The engineer would request access, a manager would approve, and they would receive temporary credentials to assume the role and run Terraform force unlock. All of these actions would generate CloudTrail logs for a full audit trail.
Extension challenge, the GitOps pull request workflow.
State locking prevents corruption during apply, but how do you prevent developers from merging pull requests based on stale plans? Design a CI/CD workflow that guarantees every PR plan is valid and that the final apply on merge is safe. Diagram 3, Automated TerraOrm PR workflow, for example, Atlantis. This diagram shows a best-in-class GitOps workflow, step by step. It starts at step 1 when a developer pushes to a feature branch and opens a pull request in step 2. This triggers step 3, where an automation bot acquires a state lock and runs TerraOrm plan. In step 4, the bot posts the plan's output directly into the PR for review. After the team approves in step 5, the merge in step 6 triggers the bottom one last time to acquire the lock again and safely run TerraOrm apply, ensuring a fully audited and validated deployment.
The takeaway.
For any team using TerraOrm, remote state is not enough, state locking is mandatory. It is the fundamental mechanism that prevents race conditions, state corruption, and infrastructure drift. The S3 backend with a DynamoDB table for locking is the canonical, production-ready pattern on AWS. Quick quiz: the DynamoDB table used for TerraOrm locking requires only one attribute for its primary key. What is that attribute's name? Drop your answer below. Next, we will tackle a serverless-specific challenge that hits every growing application. Your Lambda deployment fails because the package has exceeded its size limit. We will explore how to solve this with Lambda layers.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked and system design. Required for your AWS and DevOps jobs interviews like AWS Cloud Migration Specialist jobs, AWS Cloud Financial Analyst jobs, AWS Solution Architect jobs, Cloud Security Engineer jobs, Kubernetes Admin or Engineer or Architect or Developer jobs, DevOps ISE Engineer jobs, DevOps Metrics and Observability Engineer jobs, DevOps CI or CD Engineer jobs, AWS DevOps Engineer jobs, Cloud DevOps Engineer jobs, AWS Java or Python Developer jobs, DevOps Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Scenario 13, the bloated Lambda catastrophe.
Your data science team has built a powerful Python function using pandas and NumPy. The code is only 100 lines. You go to deploy it via your CI/CD pipeline, and the deployment is instantly rejected. The error exceeds the maximum allowed size. This is not a bug, it is a fundamental architectural constraint of serverless functions, and knowing how to solve it properly is a hallmark of a skilled cloud engineer. This failure occurs because AWS Lambda imposes hard limits on deployment package size, 50 megabytes for the compressed .zip file and 250 megabytes for the uncompressed code and dependencies. While your own function code is small, popular libraries like pandas, NumPy, or even large parts of the AWS SDK can be enormous. When you package them all together, you easily breach this limit. The solution is not to remove functionality, but to architecturally decouple your code from its dependencies using Lambda layers. Diagram 1, Monolithic Package Breaches Size Limit. This diagram visualizes the failure. On the left is the single, monolithic function.zip. Inside, you can see the small app.py is dwarfed by the huge pandas and NumPy libraries, highlighted in red. The red dashed arrow shows this oversized package attempting to deploy to AWS Lambda, but it is blocked by the glowing red wall, which explicitly labels the AWS Lambda 50 MB zip limit. The package is simply too large to pass, causing the deployment to fail.
The error message is direct and unforgiving.
Request entity too large exception. Unzipped size must be no larger than 262144000 bytes. Before, the monolithic packaging approach. Disclaimer, always test code in a non-production environment. The problem begins here. The target /flag tells pip to install all dependencies directly into the current working directory, alongside your own function code. This second command then zips up everything in the current directory, your code and all the massive libraries, into a single, monolithic archive. This is what breaches the size limit. After, decoupled code and dependency layers. Disclaimer, always test code in a non-production environment. First, we create a very specific directory structure. Lambda requires this python/lib/python3.9/site-packages path so its runtime knows where to find the modules. We install the heavy dependencies here. Next, we create a dependencies.zip containing only the libraries. This is our Lambda layer package. Separately, we create a tiny function.zip that contains only our application code. Finally, in our infrastructure as code template, we deploy the function and reference the layer. AWS will merge them at runtime. This approach is architecturally superior. It separates the frequently changing function code from the rarely changing, heavy dependencies. This results in faster uploads for your function code and allows dependencies to be shared across multiple functions. At runtime, the Lambda service virtually mounts the layer's content into the /op directory of the execution environment, making the libraries available to your code. Diagram 2, Separate Packages, combined at runtime. With the layer-based approach, the deployment is successful. On the left, we now have two distinct packages. The top package, dependencies.zip, is sent via the upload layer path. The bottom package, function.zip, containing only our code, is sent via the upload function path. Both green arrows successfully reach the AWS Lambda service. As the icon on the right shows, Lambda then logically combines the layer and the code at runtime, creating a single, functional execution environment.
Pro tip, pin your layer versions.
In a senior-level discussion, always state that you must pin your function to a specific, immutable version of a Lambda layer, for example, mylayer 3. Never reference :latest. This prevents a scenario where a new, potentially breaking version of a shared layer is published and automatically picked up by your function, causing unexpected production failures. Versioning provides stability and predictable deployments.
Follow-up question 1. Your zipped function and layers are under the limit, but you still get the unzipped size must be no larger than 250 megabytes error. How do you debug and fix this?
Answer: this means the contents are highly compressible. The fix is to prune the dependency package before zipping. You would run commands to remove unnecessary files, such as __pycache__ directories, .pyc files, and test suites that are often included in packages, for example, find name, tests, type D, exec rm, rf, plus. This can significantly reduce the unzipped size without affecting functionality.
Follow-up question 2. Your organization has 50 Python functions that all use the same pandas/NumPy layer. What is the best way to manage and distribute this layer?
Answer: the best practice is to create a dedicated, shared layers CI/CD pipeline. This pipeline's sole responsibility is to build, test, and publish blessed versions of common layers. It can publish the layer to a central AWS account and use resource policies to grant cross-account access to other development teams. This prevents each team from rebuilding the same layer and ensures everyone uses a standardized, security-scanned set of dependencies.
Follow-up, curveball: can using Lambda layers negatively impact your function's cold start performance, and if so, how would you mitigate it?
Answer: yes, it can. A large layer adds to the time it takes for the Lambda service to download and extract the code into a new execution environment. While often negligible, for latency-sensitive applications, this can be an issue. The primary mitigation is AWS Lambda's provisioned concurrency, which keeps a specified number of execution environments warm and ready to go, completely bypassing the cold start. A secondary mitigation is to optimize the layer itself by keeping it as small as possible.
Extension challenge: breaking the 250 megabytes barrier.
You are working on a machine learning inference function that requires models and libraries exceeding the 250 megabytes unzipped limit, even with layers. What is the modern, definitive AWS solution for deploying this function? Diagram 3: Lambda Container Image Workflow. This diagram shows the modern solution for large workloads. The process starts on the far left with a Docker file. This file is the input to the CI/CD pipeline, which executes Docker build and Docker push. The resulting container image, tagged v1.2.0, is stored in the ECR registry. Finally, the green arrow labeled Deploy from Image URI shows the AWS Lambda service pulling this container image directly from ECR to serve as the function's runtime, completely bypassing zip file limits.
The takeaway:
Lambda size limits are a feature, not a bug, encouraging lean functions. For dependency management, Lambda layers are the first and most common solution. They decouple code from dependencies. When your needs exceed the absolute limits of the zip-based model, the next architectural step is to embrace Lambda container image support for enterprise-scale workloads. Quick quiz: a single Lambda function can use up to how many layers at once? Let me know your answer in the comments. Next, we will tackle a critical operational issue that can bring your production system to a halt: CI/CD failures due to API rate limiting when integrating with services like GitHub and AWS. We will explore a robust architectural fix.
Scenario 14: the rate limiting brick wall.
It is release day. Your organization's 50 microservices all kick off their deployment pipelines at once. Suddenly, half of them start failing with a cryptic API rate limit exceeded error. The builds aren't even starting. Your entire release is blocked, and productivity grinds to a halt. This is not a code issue, it is a scalability failure of your CI/CD platform. How do you architect a solution that can handle this load? This critical failure happens when you rely on the default, shared infrastructure of services like GitHub Actions. When a GitHub-hosted runner executes a job, it makes API calls to GitHub and AWS from a shared IP address pool used by thousands of other GitHub customers. To prevent abuse, GitHub and AWS enforce strict API rate limits on these shared IPs. During a high-traffic event, like a company-wide release, your organization's collective pipelines can easily exhaust this shared quota, leading to widespread, intermittent failures. Diagram 1: Shared runners hitting API rate limits. This diagram perfectly visualizes the traffic jam. On the left, numerous jobs are executing on the shared GitHub-hosted runners. All their outbound traffic, represented by the red dashed line, is funneled through the shared GitHub NAT gateway, which has a single shared IP. Because this IP is used by thousands of tenants, it quickly exhausts its quota, hitting the glowing red API rate limit wall. This blocks legitimate requests from reaching the GitHub and AWS APIs on the right.
The error will appear in your GitHub Actions logs.
Error: API rate limit exceeded forward IP_address. You have exceeded a secondary rate limit. Please wait a few minutes before you try again. Before, the default GitHub hosted runner. Disclaimer, always test code in a non-production environment. This single line is the source of the scalability problem. Ubuntu latest tells GitHub to provision a runner from its massive, shared, multi-tenant fleet. While convenient, this means you get no dedicated IP address, no control over the underlying network, and you are subject to the collective API usage of everyone else on the platform. After, the scalable self-hosted runner. Disclaimer, always test code in a non-production environment. The fix is an architectural shift, reflected in this simple change. By specifying self-hosted, we are telling GitHub Actions to delegate this job to a runner that we control and have registered with our organization. This runner now operates from within our own AWS account, with its own dedicated IP address and networking, completely bypassing the shared, rate-limited infrastructure. Self-hosted runners are compute instances, EC2, containers in ECS or EKS, that you run in your own AWS account. They have an agent installed that pulls GitHub for jobs. Since these runners make API calls from your VPC, they use your account's dedicated network interfaces, like a NAT gateway. This means your API calls to AWS never leave the AWS network, using VPC endpoints, and calls to GitHub originate from your unique IP, giving you a dedicated, unshared rate limit quota. Diagram 2, Self-hosted runners with dedicated IPs. With the new architecture, the bottleneck is gone. The entire execution is now happening inside your AWS VPC, outlined in orange. A fleet of self-hosted runners, runner 1, 2, and 3, sends its traffic through your company NAT gateway. As the label indicates, this gateway has a dedicated IP. Because this IP is used exclusively by your organization, its traffic, represented by the solid green arrow, flows unimpeded to the APIs, completely avoiding the shared rate limits.
Pro tip, discuss ephemeral and auto-scaling runners.
In a senior interview, do not just say, self-hosted runners. Describe a sophisticated, cost-effective implementation. Mention using a solution like the Actions Runner Controller for Kubernetes or a custom EC2 auto-scaling group. This creates ephemeral, auto-scaling runners. A new, clean runner is created for each job and destroyed afterward. This is more secure, no leftover secrets, and more cost-effective. You only pay for what you use, than a fleet of static, always-on EC2 instances.
Follow-up question 1. What are the primary security considerations when using self-hosted runners, especially for public repositories?
Answer. The main risk is a malicious pull request executing arbitrary code on your infrastructure. To mitigate this, you must never use self-hosted runners for public repositories without strict controls. Best practice is to use them only for private repositories and implement ephemeral runners that are destroyed after each job. Additionally, the runner's IAM roles should be tightly scoped with least privilege permissions to limit the blast radius of a potential compromise.
Follow-up question 2. How can you optimize network costs and performance for self-hosted runners in AWS?
Answer. You should place VPC interface endpoints for key services like ECR, S3, and Secrets Manager within your VPC. This ensures that traffic from your runners to these AWS services stays on the private AWS backbone and never traverses the public internet via your NAT gateway. This is faster, more secure, and significantly cheaper as it avoids NAT gateway data processing charges.
Follow-up, curveball. Your company wants to use a single fleet of self-hosted runners to serve CI/CD jobs for multiple business units, but you need to guarantee that Business Unit A's jobs cannot access Business Unit B's secrets or deploy to their environments. How?
Answer. This requires a dynamic, just-in-time permissions model. You would assign a very minimal, baseline IAM role to the runner instance itself. Then, at the start of each job, you would use GitHub's OIDC provider to exchange a GitHub-issued JWT for short-lived, temporary AWS credentials. The key is that you configure the IAM role to be assumed based on the repository that triggered the job, repo:/repo.a:/ref:/ref/head/main. This ensures that the job only receives permissions specific to its own repository, creating a secure multi-tenant runner environment.
Extension challenge, the hybrid runner model.
Self-hosted runners are powerful but have operational overhead. GitHub-hosted runners are convenient but have limits. Design a hybrid CI/CD strategy that uses both, optimizing for cost, speed, and security across different types of workloads. Diagram 3, Hybrid Runner Strategy. This diagram shows an intelligent, hybrid routing strategy. A GitHub Actions workflow is triggered on the left, which leads to a job router decision point. From here, the workflow is split. Simple/non-sensitive jobs are sent to the GitHub-hosted runners to leverage their convenience and cost-effectiveness. In contrast, complex/sensitive jobs are routed down to the self-hosted runners inside your AWS VPC to take advantage of their security and high-performance capabilities. This approach gives you the best of both worlds.
The takeaway.
API rate limiting is a scalability problem that signals you have outgrown the public, shared CI/CD infrastructure. The architectural solution is to adopt self-hosted runners, which move the execution into your own controlled network environment. For enterprise-grade solutions, these runners should be ephemeral, auto-scaling, and leverage fine-grained IAM controls for security. Quick quiz: to use AWS OIDC with GitHub Actions for passwordless auth, what is the subject claim you need to configure in the IAM roles trust policy? Let me know below. Next, we will dive deep into the world of Kubernetes with a very common and difficult pipeline failure, an EKS rolling update that fails because of pending pods and misconfigured IAM roles. We will solve it with IRSA.
Scenario 15, the EKS image pullback off cascade.
Your CI/CD pipeline starts a rolling update for your microservice on EKS. The pipeline reports deployment successful. But when you check the cluster, you see a disaster. The new pods are stuck in an image pullback off or crash loop back off state, while the old pods have been terminated. Your service is completely down. This is a top-tier Kubernetes interview question that separates engineers who just deploy from those who truly understand the cloud-native security model. This catastrophic failure occurs because of a permissions disconnect between the Kubernetes and AWS IAM control planes. By default, pods running on an EKS node inherit the IAM permissions of the EC2 instance, the node role. This is a massive security risk and bad practice. The modern, secure approach is to grant IAM permissions directly to Kubernetes service accounts. If your pod needs to pull an image from ECR or fetch a secret from Secrets Manager, its service account needs an associated IAM role with those specific permissions. Without it, the AWS API calls from within the pod are denied, causing it to fail and get stuck in a pending state. Diagram 1, Pod denied access to AWS resources. This diagram shows the classic permissions failure. Inside the orange box representing the EKS node, our application, pod, is trying to start. The dashed red arrow shows it attempting to perform a ECR::PULUMI action on Amazon ECR. However, the request is blocked by the red IAM shield. The explanation bubble below makes it clear: access denied, pod is using the node's generic role. This shows that the pod's identity is tied to the underlying node, which lacks the specific, granular permissions required.
You will see these errors with kubectl get pods.
Status, image pullback off status, crash loop back off, if the app starts but cannot get secrets or config. Before, the unannotated service account. Disclaimer, always test code in a non-production environment. The manifest correctly creates a Kubernetes service account and assigns it to the pod. However, this is a Kubernetes-only object. It has no link to the AWS IAM world, so it has no AWS permissions. After, the IRSA-enabled service account. Disclaimer, always test code in a non-production environment. This annotation is the entire fix. It is the magic that links the Kubernetes service account to a specific IAM role. This is the core of IAM roles for service accounts, IRSA. When a pod uses this service account, the EKS control plane will automatically provide it with temporary AWS credentials for the specified IAM role, granting it the precise permissions it needs. For IRSA to work, two prerequisites are required. 1. The EKS cluster must have an OIDC identity provider enabled. 2. The IAM role being assumed must have a trust policy that allows the EKS OIDC provider to perform STS:"assume role with web identity. This annotation completes the chain, allowing a pod to exchange its Kubernetes token for powerful, short-lived AWS IAM credentials. Diagram 2. Pod securely accesses AWS resources via IRSA. With IRSA, the flow is secure and successful. The diagram breaks down the four-step process. Step 1, the pod gets its Kubernetes token. Step 2, it presents this token to the EKS OIDC provider, which uses it to call assume role with web identity on AWS STS. Step 3, STS validates the token and sends temporary AWS credentials back to the pod. Finally, in Step 4, the pod uses these new, authorized credentials to successfully pull its image from Amazon ECR, allowing it to start correctly.
Pro tip: automate role creation with IAC.
In a senior interview, explain how you would manage IRSA roles at scale. You would not create them manually. You would use a Terraform module or CloudFormation template that creates both the IAM role, with the correct OIDC trust policy, and the Kubernetes service account, with the correct annotation, in a single, atomic operation. This prevents configuration drift and ensures the ARN in the annotation always matches a real, correctly configured role.
Follow-up question 1. What is the main security advantage of using IRSA over attaching policies to the EKS node role?
Answer: the principle of least privilege. Attaching policies to the node role means every single pod on that node gets those permissions, whether it needs them or not. This is a huge security risk. IRSA grants granular permissions on a per-pod basis. A pod running your application gets ECR access, while a pod running Jinx in the same node gets no AWS permissions at all. This dramatically reduces the blast radius of a container compromise.
Follow-up question 2. You have set up IRSA correctly, but the pod is still failing with access denied. Where do you look to debug?
Answer: there are three key places. First, kubectl logs on the pod itself may show the exact API call that failed. Second, kubectl describe pod will show if there are any events related to the service account. Third, and most importantly, check AWS CloudTrail. Search for the assumed role's name, myAppEKS role, and you will find the exact API call that was denied, the error message, and the source IP, which is the definitive ground truth for debugging IAM issues.
Follow-up: curveball, your application needs to access an S3 bucket in a completely different AWS account. How do you configure IRSA to make this work?
Answer: this is a two-step, cross-account IRSA configuration. First, you create the IRSA role for the pod in the EKS account as usual. This role's IAM policy, however, will not grant S3 access directly. Instead, it will grant STS:"assume role permission on a second role in the target S3 account. Second, in the S3 account, you create another IAM role that has permission to access the bucket. This second role's trust policy must allow it to be assumed by the first IRSA role. The application code would then need to make two STS calls, one to get the IRSA credentials, and a second one to assume the cross-account role.
Extension challenge: the external secrets operator.
Your application needs a dozen secrets and config values from Secrets Manager and Parameter Store. Managing these as environment variables in your deployment manifest is cumbersome and insecure. How do you architect a more cloud-native, scalable, and secure solution? Diagram 3, External Secrets Operator, ESO, Workflow. This diagram shows the powerful ESO pattern. On the left, a developer defines a kind, external secret custom resource, sending a reconcile request to the cluster. Inside the EKS cluster, the external secrets operator, which has its own RSA access to AWS Secrets Manager, receives this request. It fetches the secret and then creates a native Kubernetes kind, secret. The application pod then simply mounts this native secret, completely abstracting away any need for the pod itself to have AWS credentials.
The takeaway.
Pods getting stuck during a rolling update are almost always due to an IAM permissions failure. The modern, secure, and definitive solution is IAM roles for service accounts, IRSA. It allows you to bind AWS IAM roles directly to Kubernetes service accounts, granting your pods fine-grained, least privilege access to the AWS resources they need, and nothing more. Quick quiz: for IRSA to work, the EKS OIDC provider URL must be added to the trust policy of the IAM role. How do you find your cluster's unique OIDC provider URL? Let me know. Next, we will address a subtle but critical problem in multi-region deployments: infrastructure drift. We will explore how to detect and prevent a scenario where your EU and US stacks are no longer identical.
Scenario 16, the phantom of multi-region drift.
Your company has a global, multi-region application for disaster recovery. Your pipeline successfully deploys the latest IAC update to both US East 1 and EU West 1. Weeks later, a user in Europe reports a bug that no one in the US can reproduce. After hours of debugging, you discover the cause: a hotfix was manually applied to an S3 bucket policy in the US region, but not in Europe. Your stacks are no longer identical. This is infrastructure drift, a silent killer of reliability, and you must know how to architect a defense against it. Infrastructure drift is the divergence of a deployed environment from its definition in code. It is often caused by urgent manual changes, out-of-band configuration updates, or failed partial deployments. In a multi-region setup, this is exponentially more dangerous because it breaks the fundamental assumption of architectural consistency. A deployment that succeeds in one region might fail in another due to an unforeseen difference, and application behavior can become unpredictable. The solution is a two-pronged strategy: proactive prevention during the CI/CD pipeline and reactive detection of any drift that slips through. Diagram 1: Undetected infrastructure drift. This diagram shows the dangerous, unknown state of drift. On the left, our infrastructure as code template defines a state with just an EC2 instance and an RDS database. This is correctly deployed to the region, EU West 1. However, in the region, US East 1, manual hotfix has been applied, adding a lambda function that is not defined in code. Crucially, there is no feedback loop. The IAC tooling is completely unaware that the US region has diverged, breaking the consistency of the multi-region setup.
The symptom is not an error, but a production mystery.
An application feature works in one region but fails with a subtle, access denied or resource not found error in another. Before, the blind apply pipeline. Disclaimer: always test code in a non-production environment. This is a blind deployment. The pipeline command simply tells the CDK to push the defined state to AWS. It has no step to check the current state of the target environment before acting. If there's a manual change, the CDK might either overwrite it unknowingly or fail because the existing state is unexpected. After, the proactive and reactive defense. Disclaimer: always test code in a non-production environment. This is the proactive fix. We run CDK diff before deploying. This command compares our code to the deployed stack and will exit with a non-zero status code if there are any differences, that is, drift. The exit 1 immediately fails the pipeline if drift is detected, forcing a developer to investigate before deploying. This is the reactive defense. We enable AWS config and a specific managed rule. This rule continuously monitors our CloudFormation stacks. If anyone makes a manual change to a resource managed by the stack, AWS config will flag the entire stack as drifted and can send an alert, giving us immediate visibility of out-of-band changes. This combined strategy provides defense in depth. The CDK diff or Terraform plan in the pipeline is your first line of defense, preventing deployments on top of a drifted state. AWS config is your second line, a persistent monitoring and alerting system that catches any manual changes made outside the pipeline, ensuring you are never flying blind. Diagram 2, Comprehensive Drift Detection and Prevention. With the full solution, we now have a complete feedback loop. The central CI/CD pipeline performs a proactive check, running CDK diff against both regions. The check against EU West 1 returns no drift white heavy checkmark, allowing a deployment. Concurrently, the AWS config service provides reactive monitoring. When the manual hotfix is applied to US East 1, the red arrow shows that AWS config immediately flags this as drift detected. It then sends a notification to the alerts/dashboard, ensuring the operations team has immediate visibility of the unauthorized change.
Pro tip: discuss infrastructure immutability.
In a senior interview, elevate the conversation to architectural philosophy. State that your goal is immutable infrastructure. Instead of patching a running environment, which causes drift, you always deploy a brand new, clean environment from code and then shift traffic to it, for example, blue or green deployments. This philosophy treats infrastructure as disposable and replaceable, which is the ultimate defense against configuration drift.
Follow-up question 1. How can you automatically remediate drift detected by AWS config?
Answer: you can use AWS Systems Manager automation documents. You would configure the AWS config rule to trigger an event bridge event when a resource becomes non-compliant. This event would then invoke an SSM automation runbook. For a CloudFormation managed resource, the runbook could be configured to redeploy the entire stack, effectively overriding the manual change and bringing the resource back into compliance with the code.
Follow-up question 2. CDK diff is a pre-deployment check. What's the difference between this and CloudFormation's own change sets?
Answer: CDK diff is a developer-facing tool that shows a semantic, easy-to-read comparison between the CDK code and the deployed state. A change set is a formal CloudFormation object that represents the precise, low-level API calls that will be made to update a stack. The pipeline should use both: run CDK diff first for a quick sanity check, then generate a change set for a final, authoritative preview of the changes, and finally execute that change set.
Follow-up: Curveball, your company has a mix of CloudFormation managed resources and legacy, manually created resources. How can you get a unified view of configuration drift and compliance across your entire AWS account?
Answer: this is a perfect use case for AWS config conformance packs. A conformance pack is a collection of AWS config rules and remediation actions that can be deployed as a single entity across an organization. You would create a custom pack that includes the CloudFormation drift detection rule, as well as other rules that check for compliance on all resources, regardless of how they were created, for example, s3_bucket_public_read_prohibited. This gives you a single pane of glass for compliance across both IAC-managed and unmanaged resources.
Extension challenge: policy as code for drift prevention.
Reactive detection is good, but true prevention is better. How can you proactively prevent a developer or process from making a manual change that would cause drift in the first place? Diagram 3, Preventative Controls with Service Control Policies, SCPs. This diagram shows the ultimate preventative control. At the top, within the AWS organization root, a service control policy is attached, which explicitly denies the S3:put_bucket policy action. In the member account below, a developer role attempts to make this exact call to an S3 bucket. However, the request is intercepted at the organizational boundary, as represented by the red guardrail. The large "Denied by SCP" stamp shows that the action is blocked before it is even evaluated by IAM, proactively preventing the drift from ever occurring.
The takeaway.
Multi-region drift is a silent threat to reliability. A robust defense requires a two-layer strategy: proactive prevention within your CI/CD pipeline using diff/plan commands, and reactive detection across your accounts using monitoring tools like AWS config. For maximum control, implement preventative guardrails with service control policies. Quick quiz: which AWS config feature lets you query the current and historical configuration state of all your resources using standard SQL? Let me know in the comments. Next up, we will troubleshoot a frustrating on-premise deployment issue: code deploy failing on an EC2 instance because of an outdated or stopped agent. This is a must-know for any hybrid cloud environment.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your AWS and DevOps jobs interviews like AWS Cloud Migration Specialist jobs, AWS Cloud Financial Analyst jobs, AWS Solution Architect jobs, Cloud Security Engineer jobs, Kubernetes Admin or Engineer or Architect or Developer jobs, DevOps ISE Engineer jobs, DevOps Metrics and Observability Engineer jobs, DevOps CI or CD Engineer jobs, AWS DevOps Engineer jobs, Cloud DevOps Engineer jobs, AWS Java or Python Developer jobs, DevOps Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Scenario 17, the ghost in the EC2 machine.
You are managing a fleet of EC2 instances for a legacy application. Your code pipeline build succeeds, and the deployment kicks off. You watch the code deploy console, but the deployment to your target instances is stuck on pending and eventually times out. The instance itself is running and healthy. What invisible component has failed? This is a classic EC2-based deployment problem that every hybrid cloud engineer must know. This failure occurs because code deploy uses a push-based model for EC2 deployments, which relies on a small daemon called the code deploy agent running on each target instance. This agent is responsible for pulling the code deploy service for new deployments, downloading the application revision from S3, and executing the lifecycle event hooks defined in your appspec.yml file. If this agent is not installed, not running, or is an outdated version that cannot communicate with the service, the instance is effectively a black box to code deploy, and the deployment will hang until it times out. Diagram 1, code deploy agent is missing or stopped. This diagram shows the communication breakdown. The AWS code deploy service on the left attempts to send a deployment job, represented by the dashed red line. The job is targeted at the EC2 instance on the right. However, inside the instance, the code deploy agent is shown with a red X and labeled agent inactive. Because the agent is not running to listen for commands, the deployment job is never received, causing the pipeline to hang and eventually fail.
The error in the code deploy console is often vague.
Deployment failed. The overall deployment failed because too many individual instances failed deployment. Check the instance agent status. Before, the unmanaged EC2 instance. Disclaimer: always test code in a non-production environment. The core of the problem is often in the instance's creation process. The user data script, which runs on first boot, might configure the web server or other software but completely omits the steps to install and enable the code deploy agent. As a result, when you SSH into the machine and check the service status, you will find that it is either not installed or not running, making it invisible to the code deploy service. After, automating agent installation and health. Disclaimer: always test code in a non-production environment. First, we look at the proactive solution for new instances. This block of commands installs prerequisites like Ruby, downloads the official agent installer from S3, makes it executable, and runs the installation automatically. The final command in the proactive setup ensures that the agent service is started immediately after installation, making the instance deployment ready as soon as it boots. For an existing machine that's misbehaving, this second block provides the manual fix. These commands will install or update the agent directly and then start and verify its status, bringing it back online for deployments. Automating the agent's installation and ensuring it is enabled as a system service is the key to reliable EC2 deployments. This transforms your instances from unmanaged pets into managed, predictable cattle that are always ready to receive deployments from the central code deploy service. Diagram 2, Code Deploy Agent is active and polling. With the agent running, the communication model is restored. Inside the EC2 instance, the agent status is now a green checkmark, agent active. This active agent now initiates the connection, as shown by the top green arrow, by polling for jobs from the AWS Code Deploy service. When a job is available, the service responds with the job details, as shown by the bottom green arrow. This establishes the two-way communication needed for a successful deployment.
Pro tip: debug with the agent logs.
In an interview, if they ask, "How do you debug a failing deployment script?" the expert answer is to check the agent's logs on the instance itself. The main log file is at /var/log/aws or codedeployagent/codedeployagent.log. This file contains the detailed stdut and str of every lifecycle hook script, which is the ground truth for why a script might be failing even if the agent itself is running.
Follow-up question 1. The agent is running, but deployments still fail. What is the most likely cause?
Answer: this almost always points to an IAM or networking issue. First, check that the EC2 instance has an IAM instance profile attached, and that the associated role has a policy allowing it to s3:getObject from the code deploy artifact bucket. Second, if the instance is in a private subnet, ensure it has a route to the S3 and code deploy service endpoints, either via a NAT gateway or, more securely, VPC gateway and interface endpoints.
Follow-up question 2. How can you manage and automate the update of the code deploy agent across a large, existing fleet of instances without manually SSHing into each one?
Answer: this is a perfect use case for AWS Systems Manager. You would use the Run command feature to execute a shell script on all instances tagged for your application. The script would contain the commands to update and restart the code deploy agent. For a fully automated solution, you could use SSM State Manager to define a desired state configuration that specifies the required version of the agent, and State Manager will automatically enforce this configuration across your entire fleet.
Follow-up: curveball: your application requires a graceful shutdown, needing 30 seconds to finish processing in-flight requests before the old version is stopped. How do you configure code deploy to handle this?
Answer: you would handle this in your appspec.yml file. You would create a script for the application stop lifecycle event. In this script, you would send a SIGTERM signal to your application process, which tells it to stop accepting new connections but continue processing existing ones. The script would then sleep for 30 seconds before exiting. You also need to configure a timeout in the application stop hook definition in the app spec file to ensure the agent does not kill your script prematurely.
Extension challenge: hybrid on-premises deployments.
Your company has a hybrid cloud strategy, with some servers running in your on-premises data center. How can you use the same AWS code deploy pipeline to deploy your application to both your AWS EC2 instances and these on-premises servers? Diagram 3, Unified Hybrid Deployments with Code Deploy. This diagram shows the unified hybrid model. At the top, a single AWS code deploy service manages a deployment group. This group contains resources from two different locations. On the left is the AWS cloud with its native EC2 instances. On the right is an on-premises data center. For the on-prem server to be managed, it must have both the SSM and code deploy agents installed. As the text indicates, it then registers with AWS Systems Manager to become a managed instance, allowing it to be seamlessly included in the same deployment group as the cloud resources.
The takeaway:
for EC2/on-premises deployments, the code deploy agent is the heart of the system. If it is not running, your instance is unreachable. The robust, architectural solution is to automate its installation and management as part of your instance provisioning process, using tools like EC2 User Data, Golden AMIs, and AWS Systems Manager for fleet-wide control. Quick quiz: what is the name of the YAML file that you must include in your application source code to tell the code deploy agent how to deploy your application? Let me know below. Next, we will shift our focus to security and compliance. We will tackle a scenario where your pipeline is blocked because an image scan has detected critical vulnerabilities, and we will explore how to fix it.
Scenario 18, the CISO's emergency brake.
You are about to deploy a critical new feature. The pipeline is all green through the build and integration test stages. It is in the final pre-production stage when you get a priority alert: deployment halted, security compliance violation. The CISO has blocked the release. Your feature is now stuck behind a high-severity CVE. This is the new reality of DevSecOps, and as a senior engineer, you must architect the solution, not just fix the bug. This pipeline failure is actually a sign of a mature security posture. It is a shift-left success story. The problem occurs when an automated security scanner, integrated into the CI/CD process, discovers a known common vulnerability and exposure, CVE, in your container image. This could be in an OS package from your base image, like glibc, or a third-party library you have installed. The pipeline is configured to act as a gate, failing the build and preventing a vulnerable artifact from ever reaching production. The architectural challenge is to make this process fast, efficient, and developer-friendly. Diagram 1, Late Cycle Security Gate. This diagram shows a common but inefficient security model. The pipeline progresses linearly: 1, build image, and 2, push to ECR. Both succeed, indicated by the green checkmarks. Only after the vulnerable image is already stored in the registry does it hit the 3. Security gate. This gate, highlighted in red, discovers a flaw and blocks the release, as shown by the deployment blocked crossmark status. This late-stage discovery creates a slow and expensive feedback loop.
The scan result is a clear showstopper.
Amazon ECR scan findings: 1 critical, 5 high-severity vulnerabilities found. Finding: CVE 2023-2650 in glibc. Deployment will not proceed. Before the build and push pipeline. Disclaimer: always test code in a non-production environment. The fundamental flaw here is that we are pushing a container image to a registry without knowing if it is secure. The pipeline's only job is to build and store the artifact. Security is treated as someone else's problem, to be dealt with later in the lifecycle. After the shift-left DevSecOps pipeline. Disclaimer: always test code in a non-production environment. This is the proactive fix. We have added a new command using the open source scanner Trivi. It scans the image we just built before pushing it. The exit code 1 flag tells Trivi to fail the build if it finds any vulnerabilities of critical or high severity. Crucially, the Docker push command now only runs if the Trivi scan passes. This ensures that no image with critical vulnerabilities is ever stored in our artifact repository, making the registry a trusted source of secure images. This inline scanning approach provides the fastest possible feedback loop. The build fails within minutes, directly in the developer's pipeline logs, clearly identifying the vulnerability. This is a core tenet of DevSecOps: make security an automated, integral part of the development workflow, not a final, manual gate. The same principle applies when using other tools like Amazon Inspector, which can be triggered via an API call in the pipeline. Diagram 2, Early, Automated Security Scanning. With the improved DevSecOps pipeline, security is shifted left. After the build image stage, the process now enters a critical scan image stage. This stage acts as an automated decision gate. If no CVEs are found, the green arrow shows the pipeline proceeds to push to ECR and deploy. However, if CVEs found, the red arrow shows the pipeline is immediately diverted to a fail pipeline and alert crossmark state, providing instant feedback and preventing the vulnerable image from ever reaching the registry.
Pro tip: implement a vulnerability exception process.
In a senior-level interview, demonstrate operational maturity. Explain that simply failing the build is not enough. You need a formal vulnerability exception process. When a CVE cannot be immediately fixed, for example, the patch is not yet available, a developer can request a temporary exception. This would involve adding the CVE ID to a suppression file, like .triviignore, that is checked into source control. This request must be approved by the security team via a pull request, creating a time-bound, auditable record of accepted risk. This shows you can balance security with business continuity.
Follow-up question 1. Your scan fails because of a critical vulnerability in your official base image, for example, Node 18 Alpine. How do you fix this if you do not control the base image?
Answer: this is very common. The first step is to check if a newer, patched tag of the base image is available, for example, Node 18.17.1 Alpine. If not, the correct action is to report the issue to the base image maintainers and temporarily add the CVE to your suppression file with a time-bound exception. You would then configure a tool like Dependabot or RenovateBot to automatically create a pull request to update the base image in your Docker file as soon as a patched version is released.
Follow-up question 2. How do you protect against vulnerabilities in your application's own dependencies, for example, a vulnerable NPM or Maven package, which an image scanner might not detect?
Answer: this requires a different type of scanning called software composition analysis, SCA. You would add another step to your pipeline using a tool like GitHub's Dependabot, SNYK, or even Trivi's file system scanning, TriviFS. These tools specifically analyze your package.json, pom.xml, or other manifest files to find vulnerabilities in your application's direct and transitive dependencies. A comprehensive strategy requires both container scanning and SCA.
Follow-up, curveball: how would you design a system to rescan all images in your ECR registry every night and automatically alert if a new CVE is discovered for an old, already deployed image?
Answer: this is called continuous monitoring. I would use Amazon Inspector's ECR scanning capability, which automatically rescans images. Alternatively, you can use an event bridge scheduled rule, a cron job, to trigger a Lambda function nightly. This Lambda function would list all repositories, trigger a new scan for key images using the StartImageScan API, and then check the results. If a new critical CVE is found, it would publish a message to an SNS topic to alert the security team, and could even automatically open a Jira ticket for the relevant development team.
Extension challenge: software supply chain security with SPAMs.
Due to new compliance requirements, your company must now produce and store a software bill of materials, SBOM, for every deployed artifact. An SBOM is a complete inventory of every component and dependency in your software. How do you integrate SBOM generation into your pipeline and use it to enhance security? Diagram 3, SBOM Enhanced DevSecOps Pipeline. This diagram shows a modern software supply chain security pipeline. Following 1. Build image, we enter a new, highlighted stage. 2. Generate SBOM, which creates a software bill of materials. This SBOM artifact serves two purposes, as shown by the dashed purple arrows. It is sent to an SBOM repository for compliance, and it is also used as the input for the 3. Vulnerability scan stage. The rest of the pipeline then proceeds, having created a complete, auditable trail from build to deployment.
The takeaway.
A security failure in a pipeline is a success for DevSecOps. The goal is to fail fast and early. The architectural fix is to integrate automated inline scanning directly into your build process before pushing to a registry. This provides immediate feedback to developers and ensures your artifact repositories are a source of trusted, vulnerability-free images. Quick quiz: what common open-source tool can be used to generate a software bill of materials, SBOM, from a container image? Post your answer below. Next, we will solve a complex serverless architecture problem, a deployment that fails and rolls back due to a circular dependency between two of your microservices. We will explore how to break the cycle.
Scenario 19, the serverless circular dependency trap.
You are building a sophisticated serverless application. A Lambda function needs to write to an SQSQ. In turn, that SQSQ is configured to trigger a different Lambda function for processing. You model this in a single CloudFormation or SAM template and hit deploy. The deployment starts, then hangs, and finally rolls back with a cryptic error, circular dependency detected. How do you break this logical knot? This is a core architectural pattern question for serverless development. This failure is a hard constraint of declarative infrastructure as code. CloudFormation must build a directed, acyclic graph, DAG, of all your resources before it can create them. It needs to know which resource to create first. A circular dependency, or cyclic dependency, creates an impossible situation. Resource A needs the ARN of resource B to be created, but resource B needs the ARN of resource A. CloudFormation cannot resolve this paradox, so it fails the deployment. This is common in event-driven architectures where services are tightly coupled, for example, a Lambda needing a queue's ARN and the queue needing the Lambda's permission. Diagram 1, Circular Dependency Deadlock. This diagram perfectly visualizes the deadlock within a single, monolithic CloudFormation stack. On the left, Lambda has a dependency arrow pointing to SQSQB, because it depends on B's ARN. Simultaneously, SQSQB has an arrow pointing back to Lambda, because it depends on A's ARN. These two red arrows form an unbreakable circle, representing a logical paradox that the CloudFormation engine cannot resolve, thus forcing the deployment to fail.
The error in CloudFormation events is explicit.
Export _name cannot be updated as it is imported by stack_name. Please remove the dependency from the template. Before, the monolithic, interdependent stack. Disclaimer: always test code in a non-production environment. Here, Lambda A's definition requires a reference to SQSQB. This creates the first half of the dependency, A depends on B. While not fully shown, to allow Lambda A to send messages, the queue's resource policy would need to reference Lambda A. This creates the second half of the dependency, B depends on A. The result is an unbreakable A to B to a loop. After, the decoupled microstacks pattern. Disclaimer: always test code in a non-production environment. The architectural solution is to split the resources into separate stacks based on their role. We create a core infra stack that defines foundational resources like the SQSQ. Crucially, the infra stack exports the queue's ARN using a well-known name. This makes the value available to other stacks in the same region. Next, we create a separate Lambda stack for our compute resources. This microstacks approach, using CloudFormation's export or import value feature, is the canonical pattern for resolving circular dependencies. It forces you to think about the layers of your application. You deploy the foundational, less frequently changed resources first, queues, tables, event buses, and then deploy the compute and application logic stacks that depend on them. This creates a clear, one-way dependency flow that CloudFormation can easily resolve. Diagram 2, One-way dependency via cross-stack references. With the microstacks pattern, the deadlock is broken. The core infra stack is deployed first. Its outputs section exports the queue's ARN, making it globally available. The Lambda stack is then deployed. Instead of a direct reference, it uses fn::import value to consume the exported output. This creates a clean, one-way dependency graph. The Lambda stack depends on the core infra stack, but not vice versa. CloudFormation can now deploy these stacks sequentially and successfully.
Pro tip: the asynchronous event bridge decoupling pattern.
In a senior interview, propose a more advanced, event-driven solution. Instead of the Lambda needing to know the queue's ARN, it could instead just publish a generic event to an Amazon Event Bridge bus. You could then create an event bridge rule that says, when an event of type order created appears, send it to this SQ. This completely decouples the producers from the consumers. The Lambda no longer needs any reference to the queue in its code or configuration, which elegantly solves the circular dependency at an architectural level and improves scalability.
Follow-up question 1. What are the risks or downsides of using fn::import value extensively?
Answer: the main risk is that exported values create a hard dependency. You cannot delete the stack that is exporting a value, the core infra stack, if any other stack is still importing it. You also cannot change the exported value itself. This can make refactoring difficult. It is best used for stable, foundational resources that are unlikely to be destroyed or renamed.
Follow-up question 2. How can you manage the deployment order of these new microstacks in a CI/CD pipeline?
Answer: your pipeline tool must be aware of the dependency graph. In AWS code pipeline, you would define this as sequential stages: a deploy infra stage, followed by a deploy app logic stage. In a tool like Terraform, you would use Terraform_remote_state data sources, which creates the same implicit dependency and ensures Terraform apply processes them in the correct order.
Follow-up: curveball: sometimes you can break a circular dependency within a single template by changing how you create permissions. Can you give an example?
Answer: yes. The classic example is a Lambda and an SQ. The dependency is often Lambda to SQ URL and SQ policy to Lambda ARN. You can break this by creating a separate AWS::Lambda: permission resource instead of an inline queue policy. This resource takes both the Lambda name and the queue ARN as inputs. CloudFormation is then often smart enough to resolve the graph by 1. Creating the Lambda, 2. Creating the queue, 3. Creating the permission resource that links them. This works for simple cases, but splitting stacks is the more robust solution for complex applications.
Extension challenge: the shared API gateway.
You have 10 microservices, each in its own stack. You want them all to be accessible via a single, shared custom domain and API gateway, for example, api.mycompany.com/service A, api.mycompany.com/service B. How do you architect this without creating dependencies between the service stacks? Diagram 3, Shared API Gateway with VPC Link Integration. This diagram shows a highly scalable, decoupled pattern. On the left, the API stack defines the API gateway and its routes. A VPC link connects it to a central, network load balancer inside the service's VPC. The NLB then routes traffic to different target groups. On the far right, independent Service A stack and Service B stack are shown. As the arrows indicate, each service simply registers tasks with its corresponding target group. This design brilliantly decouples the API definition from the backend services, allowing them to be deployed and scaled independently.
The takeaway.
Circular dependencies are a hard stop for declarative IAC tools. The architectural solution is to break the cycle by splitting monolithic stacks into microstacks. Group resources by lifecycle and stability, for example, core infra versus application logic, and use cross-stack references, export/import value, to create a clear, one-way dependency flow. For ultimate decoupling, adopt event-driven patterns with services like EventBridge. Quick quiz: what AWS Serverless Application Model (SAM) resource can help you deploy and manage multiple, dependent stacks as a single application? Let me know below. For our final scenario, we will dive into a sophisticated deployment strategy, a canary deployment on ECS that fails and rolls back. We will explore how to fine-tune the health checks that make this powerful technique work.
Scenario 20, the overeager canary rollback.
You are deploying a new version of your service to ECS using a sophisticated canary strategy. The pipeline shifts 10% of traffic to the new canary tasks. For a few minutes, everything looks good. Then, suddenly, your monitoring dashboard lights up with alarms. Code deploy detects the failure, instantly rolls back all traffic to the old version, and fails the pipeline. Your logs show no application errors. The canary tasks were healthy, but the deployment failed anyway. Why? This is a masterclass in fine-tuning production traffic shifting. This insidious failure is often not an application bug, but a misconfiguration of the health and stability monitoring that governs the canary release. During a canary deployment, the application load balancer, ALB, and code deploy work together. The ALB sends health checks to the new canary tasks. Code deploy, in parallel, monitors a set of cloud watch alarms that you define. If any of those alarms go into an alarm state during the canary period, code deploy immediately triggers a rollback. A common cause is a health check configuration that is too aggressive for a newly started container, causing the unhealthy host count metric to spike and trip the alarm. Diagram 1, aggressive health checks trigger rollback. This diagram visualizes the premature failure. The ALB on the left splits traffic, sending most to the primary tasks and 10% to the canary task. However, it is using aggressive health checks, which the canary fails. This failure, indicated by the red dashed line, causes the unhealthy host count metric to spike. This metric triggers the canary failure alarm, putting it into a red alarm state. The alarm sends a signal to AWS code deploy, which immediately initiates a rollback, failing the deployment unnecessarily.
The key indicator is in the Cloud Watch alarm history.
Alarm_name triggered. Reason, threshold crossed, 1 data point, 2.0, 11 hours and 34 minutes, was greater than or equal to the threshold, 1.0. Before, the overly strict health check, cloud formation. Disclaimer, always test code in a non-production environment. First, looking at the target group, the health check configuration is extremely aggressive. It checks every 5 seconds and marks a target as unhealthy after only 2 failures. This gives a new container just a 10-second window to become fully healthy, which is often too short. Second, the Cloud Watch alarm is a hair trigger. It monitors the unhealthy host count and has a threshold of 1. This means the very first canary task that fails its initial, aggressive health checks will immediately trigger a full deployment rollback. After, the resilient, production-grade configuration. Disclaimer, always test code in a non-production environment. Part 1 of the fix is to make the health checks more tolerant. We increase the interval to 30 seconds and require 5 consecutive failures. This creates a much safer 2.5-minute window, giving a slow-starting container plenty of time to initialize without being prematurely failed. Part 2 is the expert-level fix. We completely change the alarms metric from unhealthy host count to HTTP code_target_5xx_count. This stops the rollback from being triggered by harmless startup delays and instead bases the decision on actual application performance, only rolling back if the Canary version produces a significant number of server errors. This two-part fix creates a robust Canary deployment. The loosened health checks on the target group ensure that healthy, slow-starting containers are not penalized. The more intelligent CloudWatch alarm ensures that rollbacks are only triggered by genuine application-level failures, like a spike in 500 errors, not harmless startup delays. This allows the Canary period to serve its true purpose, safely evaluating the performance of the new code against real production traffic. Diagram 2, Tolerant Health Checks and Business Metric Alarms. With the resilient configuration, the Canary deployment proceeds as intended. The ALB now uses tolerant health checks, allowing the Canary task to start up and become healthy, as shown by the green checkmark. Crucially, the metric being monitored is now application 5xx errors, which is in a green OK state. This stable signal is sent to AWS code deploy, which receives the all clear and proceeds with the green proceed TO 100% action, successfully completing the release.
Pro tip: use bake time for pre-warming.
In a senior interview, show your deep knowledge of code deploy by mentioning the bake time. This is a setting in the deployment configuration that tells code deploy to wait for a specified period after the Canary tasks pass their health checks but before the Canary alarms are monitored. You would use this time, for example, 5 minutes, to run warm-up scripts or allow JVMs to JIT compile hot paths, ensuring the application is fully performant before it is subjected to the critical production alarms.
Follow-up question 1. What is the key difference between a Canary and a blue or green deployment?
Answer: blue or green is about minimizing downtime and risk by deploying a full, parallel green stack and then doing a fast cutover. Canary is about minimizing blast radius and risk by gradually shifting a small percentage of real user traffic to the new version and monitoring its performance. Blue or green tests the infrastructure, Canary tests the code on a subset of users. Canary is generally considered more advanced as it allows for testing with live production traffic.
Follow-up question 2. Your Canary alarm is based on latency. How do you prevent a rollback if the new version is expected to be slightly slower due to a new feature?
Answer: this requires dynamic, baseline-aware alarms. Instead of a static threshold, for example, latency greater than 200 milliseconds, you would use a CloudWatch anomaly detection alarm. This type of alarm creates a machine learning model of your metric's normal behavior, the baseline, and only triggers if the new value is a statistically significant deviation, for example, more than 2 standard deviations, from the expected pattern. This makes your alarms resilient to normal fluctuations and gradual changes.
Follow-up, curveball: how can you implement a Canary deployment for an AWS Lambda function?
Answer: you use Lambda aliases and traffic shifting. You would deploy a new version of your Lambda function. Then, you would update a production alias, for example, myfunction:live, to use a weighted routing configuration. For example, you would configure it to send 90% of invocations to the old, stable version and 10% to the new version. You would then use CloudWatch alarms on the new version's metrics, errors, duration. Code deploy can automate this entire process, gradually shifting the weight and automatically rolling back if the alarms trigger, providing the same safety as an ECS Canary deployment.
Extension challenge: Automated Canary Analysis, ACA.
Relying on a few CloudWatch alarms is good, but a truly advanced system would analyze dozens of metrics and logs to make a go/no-go decision. How would you architect a fully automated, data-driven Canary analysis system? Diagram 3, Automated Canary Analysis, ACA, Workflow. This diagram shows a state-of-the-art ACA workflow. Logs and metrics from both the primary, baseline, fleet, and the Canary fleet are streamed into a central analysis engine. This engine performs a statistical comparison and generates a Canary score, in this case, 98/100. This score is sent to a decision gate. Because the score is greater than 95, the gate follows the green path to promote the release. If the score had been low, it would have followed the red path to rollback, enabling a truly data-driven deployment decision.
The takeaway.
A failed Canary deployment is often a monitoring failure, not a code failure. Success requires a holistic configuration. Tolerant target group health checks ensure the service can start, while intelligent, business metric-driven cloud watch alarms ensure you only roll back on genuine application failures. This combination turns Canary deployments from a risky endeavor into a powerful tool for safe, continuous delivery. Quick quiz: in a code deploy ECS deployment, which file in your source code defines the location of your ECS task definition and the app spec hooks? Let me know the answer to our final question. And that's a wrap on 20 real-world AWS DevOps pipeline failures. Mastering these scenarios, from basic IAM issues to advanced Canary analysis, will prepare you for the toughest DevOps interviews in 2025. Thanks for watching.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked and system design. Required for your AWS and DevOps jobs interviews like AWS Cloud Migration Specialist jobs, AWS Cloud Financial Analyst jobs, AWS Solution Architect jobs, Cloud Security Engineer jobs, Kubernetes Admin or Engineer or Architect or Developer jobs, DevOps ISE Engineer jobs, DevOps Metrics and Observability Engineer jobs, DevOps CI or CD Engineer jobs, AWS DevOps Engineer jobs, Cloud DevOps Engineer jobs, AWS Java or Python Developer jobs, DevOps Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links. For more exciting tips, tricks and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development, and more. That will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers, for 2 to 3 years, experienced candidates, and for 5 or above years, experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.